Somewhere between a star and the dark beyond it, in the narrow band where gravity has drawn a world so close to its sun that the two seem almost to touch, a small rocky planet hangs in a tide of light. It is not a large world. It is not a distant one. From where it orbits, its star does not look like a star at all. A distant point of cold fire set in a black field, the way our own sun appears from the outer reaches of the solar system. From this close, the star fills the sky. It fills more than the sky. It becomes the sky, a vast curving wall of light, so near and so total that the planet's entire sunward face is bathed not in sunlight, but in something older and more fundamental, the raw heat at the surface of a star, arriving across a distance so short that light covers it in under 3 minutes. To reach a world like this from Earth, a traveler moving at the speed of light might spend decades in transit. To understand how close it orbits its star, a different kind of journey is useful, not through space, but through scale, down from the familiar geometry of our own solar system into the tight, scorched ellipse of a lava world's path. In our solar system, Mercury traces the innermost orbit, the closest planet to the Sun, completing a full circuit every 88 days at a distance of roughly 36 million miles. Even Mercury, the closest thing in our neighborhood to a sun-grazed world, would look remote, almost leisurely, compared to the orbital paths of the worlds burning far beyond our system. A lava world orbits its star at a distance many times smaller than Mercury's distance from the Sun. Some orbit so close that the entire ellipse of their path would fit within the space between Mercury and the Sun, with room to spare. And they complete that orbit, 1 full year on such a world, in less than a single Earth day. Hold that for a moment. A full year in less than a day. The planet rises, crosses the face of its star, falls behind it, emerges again, and has completed an entire circuit before the night you are lying in has finished. This is where lava worlds live, not in distant cold reaches, not in the temperate middle distances where liquid water might collect in shallow pools. These are worlds pressed into the furnace zone, held so close to their host stars by gravity and orbital mechanics that the heat arriving at their surfaces is not warmth in any sense familiar to life on this planet. It is not even heat in the sense that a desert afternoon is hot. It is stellar flux, the same energy pouring from a star's photosphere, arriving with an intensity orders of magnitude greater than what the Earth receives from the Sun at noon on the longest day of summer. The surface of a lava world does not warm in that light. It melts. At the surface of such a planet, where common rock-forming minerals like olivine and pyroxene meet temperatures exceeding 1500 Kelvin, something quiet and total happens. The crystalline structure of the rock, the orderly lattice of atoms that gives a mineral its hardness and its color and its form, begins to dissolve, not instantly, not violently, the way ice becomes steam if it crosses a heat source quickly enough to boil. Slowly, the way glass softens in a furnace, first becoming pliable, then losing its shape entirely, then flowing, then spreading, then merging with everything around it into a single undifferentiated liquid. On a lava world, this process does not stop. There is no relief from the heat. The rock melts and stays melted, and the planet's entire sunward face becomes an ocean, not an ocean of water, an ocean of rock. That distinction is worth holding. The material in this ocean is fundamentally the same material that composes Earth's crust and mantle: silicone, oxygen, magnesium, iron, calcium, aluminum, combined into the family of silicate minerals that make up most of the solid rock on this planet. The difference is that on a lava world, that material is not solid. It is liquid, it flows, It carries heat. It circulates in slow, vast currents driven by temperature differences across its surface, and it spreads across an entire planetary hemisphere without ever cooling enough to freeze. The mineral world we walk on, the stone underfoot, the mountain ridgeline at the horizon, the ancient basement rock that holds everything above it, would be on a lava world's sunward face, a slowly moving sea. Olivine is a green mineral, almost translucent when cut thin, common in basaltic rock and in the volcanic deposits that form when the Earth's mantle upwells through the crust. It is familiar from beaches near volcanic islands, where it accumulates as small rounded grains in a pale green sand. On this planet, olivine is solid. Its atoms are locked in arrangement at the temperatures we experience as ordinary. But at the surface temperatures found on a lava world, temperatures exceeding 2000 Kelvin, temperatures that would vaporize steel, olivine does not hold its form. Its crystal lattice loosens, the bonds between atoms stretch and break and reform in a fluid arrangement, and the mineral becomes something else entirely, a slow, luminous melt, glowing a deep red orange, flowing as water flows, governed by the same physics as any other liquid, but composed of material that on Earth forms the bones of continents. Pyroxene, another silicate mineral common in Earth's volcanic and mantle rocks, undergoes the same transformation. The gray-green crystals of pyroxene that you might hold in your hand, cool, heavy, solid, would, at the surface of a lava world, be part of the same flowing ocean, all of it melting, all of it glowing, all of it moving. The temperature at which these transitions happen, around 1500 Kelvin for common silicate minerals, is the threshold that defines this class of world. Planets above this temperature, on their sun-facing sides, are hot enough to maintain persistent oceans of molten silicate rock. Planets below it may have hot surfaces, even partially molten regions, but they cool enough in some areas to form solid crust. The 1500 Kelvin line is a geological boundary, as real and as consequential as any boundary in planetary science. On one side of it, rock is solid. On the other, it flows. Many of these worlds' surface temperatures do not merely cross that line, they exceed it by hundreds of degrees. Some exceed it by more than 1,000. At temperatures reaching 2000 Kelvin, 2500 Kelvin, even approaching 3000 Kelvin on the most intensely irradiated examples, the magma ocean is not merely fluid. It approaches the viscosity of a warm liquid, flowing readily, evaporating partially into the thin mineral atmosphere above it, radiating so much thermal energy that the planet glows visibly in the infrared. These are not warm worlds. These are not even volcanic worlds in the sense that we mean when we speak of Io, with its sulfur plains and its lava fountains. These are worlds where the surface state is fundamentally, permanently, globally liquid, where the entire concept of solid ground does not apply to the daylight hemisphere, and has not applied for the entire duration of the planet's modern existence. The distinction between lava worlds and other kinds of extreme planets is worth drawing clearly, because this family of worlds has its own identity, separate from the more famous categories that dominate the catalog of known exoplanets. Gas giants, including the class called hot Jupiters, which are gas giant planets orbiting their stars at close distances, have no solid or liquid rocky surface at all. They are deep columns of gas and liquid hydrogen and helium held together by gravity, with no terrain to melt and no silicate ocean possible. An object made of gas can be hot, can be extreme, can have extraordinary atmospheric chemistry, but it cannot have a magma ocean because it has no rock. Lava worlds are specifically and essentially rocky, the silicate, iron-rich bodies that form through the aggregation of solid material in the inner regions of protoplanetary disks, and it is precisely their rocky nature that makes the molten surface state so striking. Rock melted, globally, persistently, by heat that never relents. At the other end of the temperature spectrum, ice worlds, planets whose surfaces are dominated by frozen volatiles, whose environments are shaped by cold rather than heat, could not be more different in every physical parameter. Ice worlds exist in the outer reaches of planetary systems, where stellar radiation is too faint to warm a surface above the freezing points of water, or carbon dioxide or methane. The physics governing them, the sublimation of ice, the dynamics of cryogenic chemistry, the preservation of organic material in cold storage, belongs to a different domain entirely. Lava worlds occupy the extreme opposite pole of the planetary temperature range. And unlike either gas giants or ice worlds, lava worlds do something else that shapes every aspect of their existence. They stop spinning independently of their stars. The process is called tidal locking, and it is a consequence of the same gravitational forces that create tides on Earth. The moon orbits the Earth so closely that Earth's gravity has, over billions of years, slowed the moon's rotation until it matches its orbital period exactly, which is why we always see the same face of the moon. The moon completes one rotation in the same time it takes to complete one orbit, and so the same hemisphere always faces the Earth. Lava worlds undergo the same process with their host stars, but more completely, more irreversibly, because they orbit so much closer and the tidal forces acting on them are so much stronger. A lava world, in a tight orbit around its star, is almost certainly tidally locked, its rotation synchronized with its orbital period, so that one hemisphere faces the star always, and the other hemisphere faces away from the star always. Always. The word is important here. On Earth, the planet's rotation carries every point on the surface through day and night in a continuous cycle, sunrise and sunset repeating over a period of 24 hours, heat arriving and then receding, warmth and cold alternating with the clock-like regularity of the turning globe. For a tidally locked planet, there is no cycle, there is no sunrise, there is no sunset. The half of the planet facing the star has been facing the star since the tidal lock first established itself, billions of years ago, and will continue facing the star for as long as the planet exists. The other half has been in darkness for the same duration and will remain in darkness for the same future span. No rotation carries any point from light into shadow, or from shadow into light. The boundary between the illuminated hemisphere and the dark one is fixed, not moving, not shifting, not subject to seasonal change or the slow drift of precession. Fixed. This means the magma ocean is itself fixed. The dayside hemisphere, the hemisphere that receives the stellar flux, the hemisphere bathed in a heat that keeps rock in a liquid state, maintains its molten character indefinitely because the heat source is always present and never pauses. The magma ocean does not freeze overnight and remelt at dawn. It does not cool during a planetary winter and recover during summer. It simply exists continuously, the same hemisphere glowing the same deep orange red, the same ocean flowing in the same persistent state for the entire geological lifetime of the planet. Billions of years of the same face turned toward the same furnace. The nightside hemisphere, receiving no stellar radiation at all, is a different kind of world entirely. The temperatures there are cold by comparison, not cold in the way that deep space is cold, not the near absolute zero of interstellar distances, but cold enough, far enough below the silicate melting point, that the surface can solidify. The same minerals that flow freely in the magma ocean of the day side can, in the dark and cold of the permanent night side, lock back into crystalline form and build up into solid rock. Where the day side is an ocean, the night side may be a frozen crust of solidified silicate, layered and ancient, carrying no light of its own, receiving no heat from its star. It is difficult to hold these two hemispheres in the mind simultaneously, because they are so different from each other, and yet they belong to the same world. They are separated not by distance, but by the fact of tidal locking, by a gravitational relationship between planet and star that has drawn a geological line across the planet's face and declared, on this side, fire, on that side, stone. The magma ocean is not the whole planet. The darkness is not a different planet. They are two halves of a single body, existing in permanent stark opposition because of where the planet sits and how it turns, or more precisely, how it does not turn. The star that holds a lava world in this tight-locked orbit is from the planet's surface nothing like the sun seen from Earth. From Earth, the sun subtends a small angle in the sky, half a degree, roughly the width of a thumbnail held at arm's length. It is bright enough to be dangerous to look at directly, bright enough to light the entire surface of the planet and cast sharp shadows, but it is still, in terms of how much of the sky it occupies, a small disk. The rest of the sky is dark by comparison. From a lava world, the host star is something else. At distances a fraction of Mercury's orbital radius, the star subtends an angle many times larger. It fills not a thumbnail's width, but something closer to the breadth of a hand, or wider. It is not a disk in a dark sky. It is a wall of light that dominates the visual field so completely that the distinction between sky and star becomes almost meaningless. The radiation arriving from that star across a gap so small by cosmic standards that it barely registers is not sunlight in the gentle, life-sustaining sense. It is stellar irradiation measured in units that dwarf what any planet in our solar system receives. The Earth receives a certain amount of solar energy per unit of surface area per second, an amount calibrated over billions of years to maintain the temperature range in which liquid water and life are possible. A lava world at 150th of Mercury's distance from its star, which is not an extreme case for this class of planet, receives stellar flux orders of magnitude greater, not twice as much, not 10 times as much, orders of magnitude, tens of thousands of times the energy per unit area that falls on Earth's surface. Under that kind of irradiation, the concept of surface temperature, as we ordinarily understand it, measured in degrees that life can tolerate, in ranges that allow for liquid water or frozen ice or breathable air, simply does not apply. The surface is not warm. It is not hot in the way that a summer day is hot. At 2000 Kelvin, 2500 Kelvin, the surface radiates heat in the infrared, the way a furnace radiates heat, because that is what it is, a planetary scale furnace, the heat from a nearby star absorbed into the rock and re-emitted as glow. And through all of this, through the molten ocean and the furnace sky and the tidally locked hemispheres and the permanent night, what is missing is noise. Not because silence is a requirement of these worlds, but because the scale of what is happening here does not announce itself with sound. The magma ocean does not roar, the star does not crackle, the tidal lock does not make a sound as it holds the planet in place. The surface of the magma ocean moves, slowly, driven by convective currents, and the motion is as quiet as the motion of anything vast and continuous, the way a deep ocean current is quiet even when it moves a cubic mile of water per second, the way a glacier is quiet even as it carries a mountain's worth of ice down slope over centuries. The scale of these processes swallows sound, the way space itself swallows sound, and what remains is only the glow and the heat and the steady, enormous, patient light of the star. There are many of these worlds scattered through the catalogs of confirmed exoplanets, hundreds of candidates identified through the dimming of starlight. As a planet crosses its star's face, their sizes and masses measured through careful, patient observation over years and decades. They orbit stars of many types, orange dwarf stars, smaller and cooler than the Sun, stars not unlike the Sun itself, occasionally even smaller and redder stars, where the habitable zone sits so close to the star that a tidally locked rocky planet might plausibly exist there without melting. The lava worlds among the confirmed exoplanet population are not exotic outliers or statistical accidents. They appear in the data with regularity because the physics that produces them, close orbits, rocky composition, extreme irradiation, is apparently not unusual. The galaxy makes these worlds readily and in abundance. The one unifying feature of all of them, across all their variations in size and mass and stellar host and orbital period, is the temperature threshold. At the surface, in the permanent noon of the dayside hemisphere, the rock is liquid. It has been liquid long enough to forget what solid felt like. It flows because it cannot do otherwise, because the heat arriving from the star exceeds, second after second after second, for billions of years, the energy that can be radiated away, fast enough to let the surface cool below the melting point. The system is in a thermal equilibrium, but it is an equilibrium at extraordinary temperatures, a balance struck between incoming stellar radiation and outgoing thermal emission at a point where the surface material is, and has always been, and will continue to be, a slowly moving ocean of molten rock. To understand what this looks like requires releasing certain assumptions that are baked into ordinary terrestrial experience. On Earth, lava, the molten rock that emerges from volcanoes, is a spectacle. It arrives from vents and fissures. It moves in flows measured in feet per hour or yards per hour. It cools and solidifies at its edges as it spreads, forming a hardening crust even while the interior remains fluid. Volcanic activity on Earth is local, a mountain, a rift, a chain of islands, and it is temporary in geological terms, even when it persists for millions of years. The magma ocean of a lava world is none of these things. It is not local. It is not arriving from somewhere else and spreading temporarily across a solid surface. It is the surface. The entire sunward face of the planet is covered in it, not as a thin film of cooling lava over solid bedrock, but as a genuine ocean, hundreds of miles deep in places, possibly, with fluid dynamics of its own and convective circulation driven by temperature gradients between its surface and its interior. The deep interior of such a world is another matter, compressed by the weight of all the rock above it, possibly solid, despite the heat at the surface. Because high pressure raises the melting point of rock, and the weight of a planetary mass, pressing down, can keep even hot material in a solid state at great depth. The magma ocean is in this sense a surface feature, though a feature that may extend many hundreds of miles downward before the increasing pressure forces the rock back into a solid phase. On the surface itself, where the pressure is low and the stellar heat is unrelenting, the liquid is total and global. Imagine standing, hypothetically, impossibly at the edge of this ocean. Not on the day side where the temperature would vaporize any conceivable material in an instant, but at the boundary between day and night, at the line where the star's light just touches the horizon at a perpetual low angle, and the air, if it can be called that, if the thin mineral vapor above the surface qualifies, is neither the full furnace heat of the day side nor the bitter cold of the permanent night. This boundary runs in a circle all the way around the planet, a great circle line of geological finality. On one side of it, the rock is liquid, glowing, moving. On the other, the same rock is solid, dark, cold, layered into formations that have been accumulating since the night side first fell into permanent shadow. The line between them does not move. It does not migrate with a season or retreat with a change in the star's output. It is drawn by the geometry of the planet's relationship to its star, and it is as fixed as the relationship itself. This is the terminator line of a tidally locked world, and it is unlike any geological boundary that exists in the solar system we know. On Earth, the terminator, the line between sunlit and shadowed surface, circles the globe once every 24 hours, never stopping, never settling. Every point on Earth's surface cycles through it twice a day. It is a dynamic, moving feature of the planet's surface lighting, not a static geological division. On a lava world, the terminator is geological. It is the line between two fundamentally different surface states, liquid on one side, solid on the other, and it does not move because the planet does not turn. The rock at the very edge of that line, in the narrow zone where the star's light arrives at the lowest possible angle, may exist in an intermediate state, partially molten, partially solid, shifting between the two as local conditions vary, as atmospheric currents carry heat from the day side, or as the magma ocean's surface flow brings fresh hot material to the boundary and cools slightly before retreating. This transition zone is a place of extraordinary geological complexity, a place where the physics of melting and solidification are continuously active, where nothing is fully one thing or the other, but the overall character of the boundary is not ambiguous. Move even a modest distance toward the day side, and the rock is unambiguously liquid. Move the same distance toward the night side, and it is unambiguously solid. The magma ocean glows right up to that line. The deep orange-red of molten silicate, the thermal emission of rock heated to temperatures that place it firmly in the range of visible light, not just infrared, but the deep red end of the visible spectrum, can be seen all the way to the horizon of the day side, all the way to the edge where the light fades and the solid begins. And on the other side, the night side surface gives back nothing, no reflected light, no thermal glow, no bioluminescence or city light or any of the other forms of illumination that make Earth's night side visible from space. The dark hemisphere of a lava world is not merely unlit the way a moonless night is unlit. It is dark the way the inside of a planet is dark, a solid mineral dark, a darkness made of stone. Between these two states, the glowing, flowing, hot, luminous day side and the cold, solid, unlit night side, the terminator line stands as the most absolute geological boundary imaginable. There is no gradual shading from liquid to solid over thousands of miles, the way Earth's climate grades from polar cold to equatorial warmth across latitudes. There is a line. On one side of it, the material that makes up the planet's surface has been liquid for billions of years. On the other side, it has been solid for the same span, and the line does not move. The light at the edge of the magma ocean, the faint, deep glow of molten silicate, visible at the very boundary between the two hemispheres, falls across stone that is cooling and stone that has long since cooled. The orange-red of the melt fades where the light of the star no longer reaches and where the heat of the ocean no longer extends. The solid night side begins in shadow and extends around the curve of the planet away from the star, dark and cold and patient, carrying in its layered formations the record of everything the night side has received, the slow rain of minerals carried on atmospheric currents from the day side, deposited over geological time into the cold dark of the permanent hemisphere, accumulating layer by layer in a kind of geological record written not in water-laid sediment but in silicate rain. That line, the terminator of a lava world, is not an edge the planet crosses. It is the planet's permanent condition. The molten ocean on one side has always been liquid. The solid crust on the other has always been dark. And between them, drawn by the mechanics of gravity and the geometry of an orbit too small and too fast to permit any alternative, the boundary holds, still, fixed and absolute, under the unmoving light of a star that has never set. In the flat, slowly rotating plane of gas and dust surrounding a young star, before any planet had yet formed, there was only the disk. It stretched outward from the newborn star in a thin continuous sheet, not empty, but not yet solid either. Grains of dust, each one smaller than the width of a human hair, drifted through that space in slow, wide orbits. They were the raw material of everything that would come after. And in the cold outer reaches of that disk, and in the warmer inner regions closer to the star's light, those grains were already beginning, almost imperceptibly, without any intention or direction, to find each other. The finding was not dramatic. Two grains of dust drifting close enough together would touch. If they touched gently enough, they would stick. The force holding them was nothing more than the same weak attraction that makes dust cling to a window in a still room, a molecular adhesion, a surface tension so small that even a breath of wind would normally undo it. But in the near silence of the protoplanetary disk, with its currents slow and its collisions gentle, the grains held. A cluster of two became a cluster of four. A cluster of four became a pebble. The pebble accumulated more grains than other pebbles, and the mass that gathered around it began to exert a gravitational pull of its own, small but real and growing. This is how planets begin. Not in fire, not in violence, but in the quiet collision of dust, and in the patient arithmetic of accumulation. The object that would one day become a world began as something you could hold in one hand, and then both hands, and then something larger than a house, and then something with its own gravity, pulling more material toward itself with every passing orbit. The disk fed it. The disk fed dozens of such growing bodies at the same time, and they grew together, competing for the same supply of dust and pebbles, and slowly accumulating rock. Inside those growing bodies, something else was beginning. The heat of accumulation, the kinetic energy of every falling grain converted into warmth on impact, was building in the interior, not quickly, but steadily. Every new grain that struck the surface and came to rest there contributed a small fraction of its energy as heat. And deep within the growing rock, a second source of warmth was at work. Certain isotopes, unstable atomic variants, forged in the depths of older stars before this solar system existed, were decaying inside the stone itself. Aluminum-26 was the most significant of these, a short-lived isotope whose decay releases energy. Locked inside the rock in the early stages of the disk's life, it warmed the interior of every growing planetesimal from within, the way a slow chemical reaction warms a compost heap in a cold field, steady and invisible and persistent. The combination of surface heating and internal warming was enough. In bodies that grew large enough, quickly enough, the interior rock began to soften. Not all of it, not immediately, but in patches, in zones of slightly elevated temperature where the heat had nowhere to go. The solid interior of the growing planet was no longer entirely solid. It was becoming something else, a slow, hot mixture, part crystalline, part molten, the boundary between them shifting as the heat accumulated. The planet was beginning to melt from the inside. This melting was not uniform. Some regions of the early interior reached the liquid state before others. Iron, which melts at lower temperatures than many silicate minerals and is far denser than the surrounding rock, began to liquefy first in these hot zones. The liquid iron could move. Heavy and dense, it had no reason to stay where it was. The pull of the planet's own gravity drew it downward, toward the center, where the mass was greatest and the inward pull most strong. Slowly, over hundreds of thousands of years, iron droplets began to descend through the rock, moving downward through any crack or softened zone they could find, like heavy rain working its way down through saturated soil. This descent released more heat as the iron fell. Gravitational energy converted into warmth, and the warmth accelerated the melting, and the melting made more paths for the iron to fall. The process fed itself. This slow sorting of materials by density is called differentiation. The word is plain enough, but the process it names is one of the most consequential things that can happen to a planet. As the iron descended toward the center, lighter materials, the silicate minerals, the calcium and magnesium compounds, the silicon and oxygen that would later form the stuff of rock, rose toward the surface. The planet was separating into layers. A metallic core was assembling itself at the center, built from iron and nickel falling inward over millions of years. Above it, the lighter silicates were accumulating in a broad, warm, increasingly fluid layer, the beginning of what would eventually become a mantle. And at the surface, the lightest and most easily melted material was spreading across the top of everything, pooling in the low places, filling the craters left by ongoing impacts from the still crowded disk. At this stage, the surface of the growing planet was not land, it was an ocean. Not of water. Water was not here yet, and the temperatures were far too high for it, but of molten silicate rock, glowing a deep orange red in the light of the young star, shifting slowly in long, broad currents driven by the heat rising from below. This was the first magma ocean, a global sea of liquid rock covering the entire surface of the planet, perhaps hundreds of miles deep, its surface radiating heat in long-wave infrared light that streamed out into space with nothing yet to stop it. The disk around the young star was still crowded. Other bodies, planetesimals, protoplanets, objects of every size from boulders to small worlds, moved through the same orbital space in paths that frequently intersected. The growing planet in its accumulation phase was still being struck. Most of these impacts were small, adding mass and heat in increments. Some were larger, and occasionally, in the long span of planetary formation, there were impacts that were not small at all. Picture two worlds approaching each other across the emptiness. One of them is already large, a growing protoplanet with its differentiated interior, its liquid iron core already assembling itself, its surface already covered in a shallow ocean of molten rock. The other is smaller, but not small, a body perhaps the size of a continent, perhaps larger, moving on an orbital path that intersects the first planet's path at a speed of several kilometers per second. The approach is slow by some measures. The collision itself, when it comes, is not. The energy released in a giant impact of this kind is not easy to hold in the mind, as a single thought. The mass of two world-sized bodies, multiplied by the square of the velocity at which they meet, the number is large, in a way that resists comparison. What it means physically is this: the surfaces of both worlds dissolve, not immediately, not in a single instant, but in the span of minutes to hours. The kinetic energy of the collision spreads through the outer shells of both bodies as heat so intense that silicate rock does not merely melt, it vaporizes. The outer layers of the impacted world flash from solid to liquid to gas in the time it takes to exhale. What remains, in the hours and days after the collision, is a globe of glowing liquid rock surrounded by a cloud of rock vapor, all of it slowly reassembling under its own gravity into a new, reshaped world. The layers that had spent millions of years carefully differentiating, the iron descending, the silicates rising, have been partly stirred back together in a few hours. The new world's surface in the aftermath is a fresh magma ocean. Not the first one. This planet may have been partly cooling, its outer layers beginning to solidify, but now fully reset. The heat of the impact has erased whatever fragile progress toward cooling had been made, and the entire outer shell of the planet is liquid again, glowing, churning, beginning the long process of cooling and crystallization once more. This is planetary formation's great reset, a giant impact that rolls back millions of years of thermal evolution and starts the countdown again. These events were not rare in the early solar system. The disk was crowded, and the orbits of the growing planets were not yet settled. The final stages of planetary formation, the period when most of the major bodies were nearly complete, but the disk still held enough debris to cause catastrophic collisions, were a time of frequent giant impacts across all the inner rocky worlds. Each impact added mass and heat. The largest of them set the thermal history of the affected world back by tens of millions of years. Some worlds were struck more than once. The record of those impacts is written in the oldest surviving rock of the solar system, in the isotopic ratios of minerals that formed and reformed in magma oceans, in the compositions of planetary cores that bear the chemistry of accreted impactors. In the long quiet that followed the last of the large impacts, a cooling began. A magma ocean in space, with no atmosphere to trap heat and no neighboring body to add energy, loses warmth quickly at first. The surface radiates heat into the dark, and the outermost layer of liquid rock, which has lost the most heat, cools toward a temperature at which it begins to crystallize. The first crystals to form in a cooling magma ocean are the minerals with the highest melting points, dense phases such as bridgmanite and iron magnesium perovskite, which solidify at the highest temperatures and sink downward through the liquid because they are denser than the surrounding melt. As these crystals descend, the surface is left slightly depleted of the elements they carried with them, and the next minerals to crystallize are different in composition. At the very surface, a thin crust tries to form. A film of solidified rock, dark and fragile, begins to appear at the top of the magma ocean in the coldest regions, the places where heat is radiating fastest into space. The film is thin. It is less stable than it appears. Underneath it, convection in the magma ocean is still active. Hot material rising from depth, spreading across the base of the crust, cooling and sinking again, an endless circulation that delivers heat from the planet's interior to its surface and prevents the crust from thickening too fast. When the crust reaches a certain thickness, the buoyant forces driving convection beneath it become strong enough to crack it and pull sections of it downward, and the thin, dark film of solidified rock breaks apart and sinks back into the melt below. and the magma ocean surface is exposed again, glowing and uncovered. This cycle, crust forming, cracking, and sinking, can repeat for millions of years. The magma ocean is not a static lake waiting passively to freeze. It is an active body in constant motion, its surface in dialogue with the cold of space above it and the heat of the planet's interior below it. Where convection is vigorous, the surface remains liquid for longer. Where it slows, the crust thickens a little before the next overturn. The solidification of a global magma ocean is not a smooth, uniform freezing from the outside in, but a slow, irregular, convection modulated process that proceeds differently in different regions of the surface. The timescales involved are long by human measure. For a planet the size of Earth, with its particular composition and internal heat, the solidification of a global magma ocean may take anywhere from a few million to perhaps 100 million years. For a larger planet, a super-Earth, twice or three times Earth's mass, the greater volume of melt and the higher pressures in the interior change the solidification sequence significantly. The minerals that crystallize at high pressure behave differently from those that form near the surface, and the resulting layered structure of the solidified mantle is more complex, more dependent on the precise path the cooling takes, more sensitive to small variations in composition. For a planet that ends up in a very close orbit around its host star, the cooling may never complete at all. The solidification of a magma ocean depends on heat being able to escape from the planet's surface faster than it arrives. On a world very far from its star, in the dark and the cold, heat escapes easily, and the magma ocean cools on its own timescale. On a world that orbits its star in a fraction of an Earth day, at a distance so small that the star's disk fills a large part of the sky, the rate at which stellar energy arrives at the sunward surface is enormous, far larger than the rate at which the planet can radiate heat away. The magma ocean on the sunward face of such a planet does not cool. It cannot cool. The incoming stellar radiation replenishes the heat as fast as the surface attempts to shed it, and the liquid rock remains liquid, not because it was recently melted, but because it is continuously and permanently kept molten by the star itself. This is the condition of the lava worlds, now known to exist beyond the solar system. They are not planets in the first moments of their formation, hot only because they have not yet had time to cool. They are planets that may be billions of years old, and that passed through their magma ocean phase long ago, and should, by all geological reasoning, have long since solidified, but find themselves locked in place beside stars, so close and so luminous that the cooling they would otherwise experience is simply not permitted. The heat arriving from the star is not an addition to their natural warmth. It is a substitute for the internal heat that has long since diminished, replacing it with external stellar energy and holding the surface in a liquid state that would, in a different orbit, be only a memory. The internal state of such a planet, beneath the surface that is held molten by its star, is uncertain in ways that matter enormously for understanding how these worlds work. If the planet has been in this close orbit long enough for its own internal heat to have largely dissipated, then the driving force for the magma ocean circulation is not internal heat rising from the core, as in a newly formed planet, but the steady input of stellar energy at the surface on the day side. The magma ocean is heated from above on one hemisphere and cooled, or at least less strongly heated, on the other. This is a profoundly different thermal regime from anything seen in the formation phase. In the early magma ocean phase, heat flows from the inside out. In a mature lava world, heat flows into the planet from the star on one side. The convective patterns inside the magma ocean, the way it circulates, the direction in which its internal currents run, all of these must be different from what a newly formed planet experiences. The magma ocean of a lava world in a stable close orbit is an ancient body being kept in a young state, driven by forces that come not from within, but from the star that holds it at arm's length. There is a planet in this solar system that once stood in a state not entirely unlike the magma ocean surface of a modern lava world. It is the planet under the listener's feet. In the first 100 million years or so after its formation, Earth was not the water covered, life bearing world it is today. It was a world of molten rock and vapor, its surface a glowing ocean of silicate melt, its sky above the magma filled with rock vapor and dense gases exhaled from the interior. The outer layers were liquid. There were no continents. There were no oceans of water. There was no stable crust thick enough to walk on, and had anything walked, it would have found the surface shifting and cracking and sinking beneath it, the magma ocean flowing across whatever fragile skin of solidified rock tried to form at the top. This is not a reconstruction built from imagination. It is a picture assembled from physical evidence, from the ages of the oldest surviving minerals, from the isotopic compositions of ancient zircon crystals that formed at the very edge of the cooling magma ocean and preserved a chemical record of the temperatures and compositions of those times. The zircon grains are survivors. They formed early, in the shallow margins of the cooling magma ocean, and they were hard and chemically stable enough to survive everything that came after, the remelting, the tectonic recycling, the long journey down and up through the mantle, and to be found, billions of years later, in the sandstone of a dry riverbed in Western Australia, where they were eventually picked up, dated, and read for their evidence. Those crystals tell a story of a surface that was cooling, of water that was already present in trace amounts, of a world beginning the long transition away from its early molten state. They are 4.5 billion years old. They are the oldest known solid material from Earth's surface, and they formed at the edge of a magma ocean that, for the Earth of that time, covered everything. The most significant event in Earth's early thermal history, the event most relevant to the magma ocean phase, came from the outside. Something large struck the young Earth. The best estimate of when this happened is about 4.5 billion years ago, not long after the solar system had finished its first wave of planet formation. The impacting body was substantial, perhaps the size of Mars, perhaps somewhat smaller, and it struck at an angle that did not simply add its mass to Earth, but instead sent much of the outer material of both bodies, impactor and Earth together, into orbit around the planet. What assembled from that orbiting material over the weeks and months that followed was the Moon. The collision itself was thermal catastrophe and geological rebirth at the same moment. The energy of the impact melted Earth's outer shell entirely. The careful differentiation that had been preceding, the iron descending, the silicates rising, the slow sorting of the planet's interior into layers, was violently disrupted. The outer portions of Earth and the impactor mixed together in the violence of the collision, and the surface of the Earth that remained was a fresh magma ocean, thousands of kilometers deep in places, its surface radiating heat into a sky full of vaporized rock. This was not Earth's first magma ocean. The planet had almost certainly passed through at least one earlier, but it was the largest, and the one that set the conditions for everything that came after. The cooling of this final magma ocean took tens of millions of years. During that time, the process of differentiation resumed. Iron descended again, silicates rose and spread. The crystallization sequence of the cooling melt produced a layered lower mantle, and above it, as the crust began to stabilize, a surface slowly emerged from the liquid state. First isolated islands of solidified rock, then broader platforms, eventually the first true crust. Above that crust, a thickening atmosphere held water vapor and carbon dioxide and other gases released from the cooling melt, and when the surface temperature finally dropped below the boiling point of water, it began to rain. Water, carried in by comets and asteroids in the period following the Great Impact, condensed from the atmosphere and fell onto the cooling rock, and Earth's first oceans, oceans of water this time, not of molten silicate, began to form. The transition from magma ocean to water ocean took tens of millions of years. It happened once, on this planet, in the first fraction of its history, and left almost no direct record in the surviving rock. The oldest traces of it are those zircon grains, and the chemical signatures in certain ancient volcanic rocks that bear the isotopic imprint of a magma ocean's crystallization sequence. The rest of the evidence has been consumed by the planet's own geological activity, subducted, remelted, recycled, and is simply gone. The magma ocean years of Earth are, in the physical record, almost entirely silent, but the physics of how a magma ocean forms and cools is not silent. It can be calculated, modeled, and constrained by the surviving evidence, and what emerges from that work is a picture of a process that is deeply familiar, in geological terms, to anyone who studies the interiors of rocky planets, because it is the same process now continuing on the exoplanets that orbit at such extreme closeness to their stars. The difference is not the mechanism, the difference is the ending. For Earth, the magma ocean ended. The star was far enough away, the cooling fast enough, the internal heat eventually low enough that the surface solidified and stayed solid, and a different kind of world was possible. For a lava world in a close orbit, the ending has not come. The process continues. The magma ocean that Earth ended 4 billion years ago is still open on the surfaces of planets, orbiting in other systems, held open not by recent formation, but by the permanent attention of a star that will not let the rock grow cold. To hold both of these images at once, early Earth glowing in its own melt, and a distant exoplanet held in the same molten state by its star, is to see the magma ocean as something more than an exotic condition of distant worlds. It is a phase, a stage in the thermal history of rocky planets, one that every rocky world may pass through during its formation, and that some worlds, by virtue of where they orbit, never leave. The physics that governs both is the same. Silicate rock at high enough temperature becomes a flowing liquid. That liquid convects, it differentiates, it cools if it can, and if the heat source is strong enough and close enough, it does not cool at all. The planet this process produces, after billions of years, locked in place beside a star, its surface still liquid, is not a world that has failed to grow up. It is a world whose thermal history has been interrupted, held at an early stage, preserved in a state that all rocky planets once knew, and that most planets quietly left behind. The magma ocean is not an ending. For most worlds, it was a beginning. For lava worlds, it has never stopped being the present. In the long, unhurried history of rocky planets, the magma ocean is the oldest chapter, and on certain worlds burning at impossible nearness to their stars, it is the only chapter there has ever been. The rock has been liquid since the beginning. It will be liquid for as long as the star continues to shine. And when the star one day dims and cools, the magma ocean will finally receive the stillness it has not known since the disk that made the planet first began to turn, the slow, patient cooling that every other rocky world received billions of years ago, arriving at last, long after everything else has settled into silence. That cooling, when it comes for a lava world, will take millions of years to complete. The surface, given the chance to radiate its heat freely into the dark for the first time, will begin to solidify at its margins, the way a puddle freezes from the edges inward on a cold night. A thin skin of crystallized rock will form. It will thicken slowly, season by imperceptible season, until the last of the magma ocean closes over and the surface is stone. The world that emerges from that process will be ancient and strange, a planet whose mantle carries the chemical fingerprint of billions of years of uninterrupted differentiation and convection, whose surface layers bear a composition unlike any solidified world in this solar system, whose geological history is a single, enormously long chapter of flowing rock punctuated by nothing, because nothing was ever cold enough to interrupt it. Somewhere in the darkness behind the star that warmed the early Earth, and behind the young sun of every planetary system now forming in the galaxy's spiral arms, the same dusty disk is gathering, and the same slow arithmetic of accumulation is beginning. The dust finds the dust. The pebbles find the pebbles. The growing bodies warm from within, and the heat of their formation softens them, and the iron descends, and the silicates rise, and the surface flows. For most of those growing worlds, the flow will one day stop. The star will be far enough away, and the cooling will be allowed, and something new will begin on the surface of the solidified rock, something unexpected, something that could not have existed on the liquid surface, something that needs the stillness of solid ground to take hold. For a few of those worlds, the ones drawn into tight, light-flooded orbits very close to their stars, the flow will not stop. The surface will go on moving, glowing, turning slowly in its great convective patterns for longer than any of us has words to hold. And the planet will wait, liquid and patient, for a cooling that has not yet arrived, resting in the state that all rocky worlds once knew. At the very beginning, when the solar system was young, and everything was warm, and nothing had yet had the chance to grow still. A planet crosses the face of its star. The star does not notice. It continues to burn, as it has burned for billions of years, pouring light outward in every direction across the indifferent dark. But for the instruments pointed at it from a small observatory on a pale world, 40 light years away, something changes. The starlight dims, just slightly. A shadow smaller than a thumbnail held against the sun moves across the star's bright face. The dimming lasts for a matter of hours. Then it passes. The star brightens again to exactly what it was before, and the instruments record the event, and somewhere in that recording is the first evidence of a world made entirely of flowing rock. This is how astronomers first confirmed that lava worlds exist, not by seeing them, but by the tiny repeating absence they produce in the light of their stars. A planet crossing its star's disk blocks a small fraction of that light. The deeper the dip, the larger the planet. The time between dips reveals how long the planet takes to complete one orbit. From those two numbers alone, the rough dimensions of an entirely unknown world can be sketched, its size, its distance from its star, and the temperature its surface must endure under that relentless close radiation. In the early decades of exoplanet astronomy, this method, patient and cumulative and quiet, opened a census of worlds that no telescope could directly see. Among them, small and dense and burning, were the lava planets. The light of the star 55 Conchoree is visible from Earth without any telescope at all. On a clear night, in the constellation Cancer, it appears as a faint point, no brighter than many others nearby, indistinguishable to the eye from any of the thousands of other stars scattered across the same region of sky. It sits about 41 light years from the Sun, near enough in cosmic terms to feel almost local, though the light leaving it tonight will not arrive here until well into the next century. Orbiting within that same system, closer to the star than any planet in our solar system comes to the Sun, is a world that completes a full year in under 18 hours. By the time a person living on Earth has woken, worked through a morning, eaten a midday meal, and begun an afternoon, that world has already circled its star once and begun again. This planet has been designated 55 Cancri Pia. It is roughly twice the width of Earth, and its mass is close to 8 times as great. Its density suggests a rocky interior, silicates, iron, the same broad categories of material from which Earth and Venus and Mars were assembled, just arranged at a different scale. But it orbits at a distance of roughly 1.5 hundredths of an astronomical unit, a number that means very little until it is compared to something familiar. Mercury, the closest planet to our Sun, orbits at about 4/10ths of an astronomical unit. The distance at which 55 Cancri orbits its star is approximately 26 times smaller than that. The star fills a portion of the sky there that would be difficult to look at if looking were possible, which it is not, because the surface beneath that sky is a slow, continuous ocean of molten silicate rock glowing at temperatures near 2,700 Kelvin. The day side of 55 Cancri sits under a permanent stellar noon. There is no morning on this world. No rotation carries it through a cycle of light and dark. Its rotation is locked to its orbital period, in the same way that the moon's rotation keeps one face always toward Earth, and for the same gravitational reason. The star tugs at the planet's slight asymmetries, slowing its spin over millions of years until the spin and the orbit synchronized, and now one hemisphere receives all the light and the other receives none. The day side melts continuously under that exposure. The night side sits in a dark that has persisted for as long as the tidal lock has held, which is most of the planet's history. Recent observations of 55 Cancri E with the James Webb Space Telescope have introduced a degree of complexity that models of bare, rocky lava worlds did not initially predict. The thermal emission data suggest that the planet may carry a volatile-rich atmosphere, a thin but real layer of gas around the planet's sunward face, rather than being entirely exposed molten rock open to vacuum. What that atmosphere is made of, how it formed, whether it is stable or slowly eroding, are questions that remain open. The best current picture is of a world more dynamically complex than a simple lava lake, one where the magma ocean and whatever sits above it interact in ways that change the planet's observable properties in ways still being sorted through. What is settled is the surface temperature, the orbital parameters, and the rocky composition. What remains conditional is the precise nature of the layer between that surface and the star's full radiation. The Kepler Space Telescope, launched in the spring of 2009, was designed to stare at a single field of stars for years at a time and record every subtle change in their brightness with a precision that no ground-based observatory could match. It watched more than 100,000 stars without looking away. In January of 2011, astronomers working with its data announced the first rocky exoplanet it had confirmed. The planet was given the designation Kepler-10b. Its orbital period is about 20 hours short of a single Earth day, not quite a full day to complete one full year. It is approximately 4.5 times the mass of Earth, and its radius is about 1 1/3 times as large. The density that follows from those numbers points unmistakably to a planet made primarily of rock and iron, not gas. Kepler-10b's estimated dayside temperature exceeds 2,500 Kelvin. At those temperatures, The minerals that make up common volcanic rock, the feldspars, the pyroxenes, the olivines, are not solid. They are liquid, and at the top of their liquid range, they approach something closer to a highly fluid melt than the slow viscous lava that pours from terrestrial volcanoes. The surface of Kepler 10b's day side, under those conditions, is not a landscape in any ordinary sense. There are no mountains, no plains, no coastlines where something dry meets something liquid. There is only the ocean, shifting slowly under the continuous thermal energy delivered from above. And above the ocean, there is whatever thin layer of mineral vapor the temperatures press up into the space above the melt. The light curve that revealed Kepler 10b is a simple thing to describe. At regular intervals of nearly exactly one Earth day, the recorded brightness of the star Kepler 10 dropped by a small precise fraction, held at that reduced level for a matter of hours, and then returned to its baseline. The pattern repeated without deviation for as long as the telescope watched. From that repeating dip in brightness, one fact was certain: something solid was crossing the star's face on a fixed orbit. Everything else, the composition, the temperature, the molten surface, required additional measurement and modeling. But the dip itself was the beginning. A shadow moving across a distant star, measured by a telescope in space, was the first sign that a world of liquid rock existed beyond our solar system. Before Kepler 10b, before the full yield of the Kepler mission had been processed, there was Corot 7b. It was found by the Corot satellite, a French-led mission that preceded Kepler, and its existence was announced in 2009, making it one of the first super-Earths for which a rocky composition could be established through actual measurement rather than inference alone. Establishing that a planet is rocky requires two separate pieces of information. A transit gives the planet's size, but to determine density, and therefore composition, the planet's mass is also needed, and mass requires measuring how strongly the planet's gravity tugs on its host star as it orbits, a small regular wobble in the star's radial velocity that can be detected in the shifting of spectral lines. For Cort 107b, both measurements were made. The transit gave the radius. The radial velocity measurements gave the mass. From those two numbers came a density consistent with rock and metal, not with gas or ice. The planet's dayside temperature is estimated near 2,600 Kelvin. It orbits its host star in roughly 20 hours. The closeness of that orbit, combined with the surface temperature it implies, places Cort 107b firmly in the category of worlds where silicate rock does not sit as a stable solid, but persists as a liquid ocean under continuous stellar bombardment. What theoretical modeling of Cort 7b's conditions has suggested is a weather system unlike anything in the solar system. The dayside, hot enough to vaporize rock, sends silicate vapor rising into the planet's thin atmosphere. Atmospheric currents carry that vapor toward the night side, where temperatures drop significantly. There, the vapor cools past the condensation point, and the silicate particles that form from it fall. On the night side of Cort 7b, if those models are correct, it rains rock, not metaphorically, actual droplets of liquefied silicate mineral, falling slowly through a thin atmosphere onto a cooler surface already covered in the accumulated deposits of previous falls. The rain is silent in any human sense because there is no medium to carry sound that a human ear could hear, but in physical terms, it is as regular and as consequential as rain falling on a terrestrial hillside, moving material from one part of the planet's surface to another in a slow, continuous cycle. The cooler regions of Cort 7b's night side, Receiving those mineral deposits over geological time would accumulate a layered surface of solidified silicate compounds, each layer laid down by a previous cycle of evaporation, transport, and precipitation, a geology built not by volcanic eruption or tectonic motion, but by the slow, repetitive fall of material condensed from its own atmosphere. Whether those layers are thick or thin, whether they are stable or reworked by the next cycle before they can consolidate, depends on variables that current observations cannot fully constrain. The picture is physically coherent, grounded in understood chemistry and thermodynamics, and it represents the best current model of what the night side of a hot, tidally locked rocky world would look like over long time. 6.7 hours. That is the length of a full year on K2 141b, the time it takes that planet to complete one circuit of its host star. 6.7 hours is shorter than most nights of sleep. In the span of a single waking day on Earth, K2 141b orbits its star more than 3 times. The orbit is so tight and the star so close that the planet's dayside temperature is estimated at roughly 3,000 Kelvin. That is a number worth sitting with for a moment, not because it is large in some abstract sense, but because of what it means in physical terms. Steel vaporizes at around 3,100 Kelvin. The surface of K2 141b's day side is hot enough that steel, if it existed there, would not melt. It would evaporate directly into gas. At 3,000 Kelvin, even the least volatile of the common silicate minerals are not merely molten, they are partially vaporized. Sodium, which has one of the lower boiling points among the elements found in rocky planets, passes from its liquid state into a gas at a temperature well below what K2 141b's day side sustains. Silicon monoxide vaporizes under the same conditions. Silicon dioxide, the compound that makes up most ordinary quartz, and is a fundamental component of nearly all silicate rock, enters the gas phase. The atmosphere of K2 141b's day side, according to detailed atmospheric modeling, is composed in significant part of these vaporized rock components, not trace amounts, but chemically significant concentrations of gaseous silicon, sodium, and oxygen compounds, rising from a surface that is simultaneously their source and their floor. That mineral atmosphere does not stay over the day side. The pressure differential between a day side heated to 3,000 Kelvin and a night side much cooler drives atmospheric winds of extreme velocity. Models of K2 141b's atmospheric circulation estimate wind speeds that may reach or exceed 5 kilometers per second at the level of the upper atmosphere, winds that would cross the entire width of Earth's atmosphere in a matter of minutes. These winds carry the mineral vapor from the sunward hemisphere toward the dark side, where the temperatures no longer support the vapor state. The gas cools, it condenses. The condensed material falls onto the night side surface, building up deposits of solid silicate and metal compounds over time, and the cycle continues, driven by the persistent thermal gradient between a day side that never cools and a night side that never warms. What K2 141b also illustrates more starkly than most lava world candidates is the extreme gradient of conditions across a single small planet. The day side, at 3,000 Kelvin, is a place where rock is a gas. The terminator, the line where the sunlit hemisphere meets the dark, marks a transition across which temperature drops by hundreds of degrees over a distance that might span no more than a few hundred kilometers of surface. On the night side, temperatures could be cool enough that silicon dioxide falls and accumulates as a solid deposit. One planet, simultaneously, is a place where rock evaporates and a place where evaporated rock falls as rain and solidifies again. The two faces are separated by a boundary no wider than a large terrestrial mountain range, but the physical states they sustain are separated by the entire range of silicate rock's possible conditions, from gas to liquid to solid, compressed into a single world. HD2 13885b presents a different kind of distance from the familiar than K2 141b's extreme temperatures suggest. The difference is in its host star. The stars around which most well-studied lava world candidates orbit are dim, cool, red dwarf stars, smaller than the Sun, less luminous, older in their energy output, and very common in the galaxy. The Sun is a yellow-white star of moderate size and temperature, and relatively few of the closest lava world candidates happen to orbit stars that resemble it closely. HD2 13885b is an exception. Its host star is a Sun-like star, similar in mass, in luminosity, in surface temperature, in spectral character to the star that lights the Earth each day. HD2 13885b orbits that Sun-like star in approximately 1 Earth day. Its size and mass place it in the super-Earth category, larger than Earth but smaller than Neptune, with a density consistent with a rocky interior. Its dayside temperature, given the stellar energy it receives at such close range, falls within the range associated with persistent magma ocean surfaces. It is not the hottest of the known lava world candidates. Its temperatures do not reach the extremes of K2 141b, but the combination of its rocky composition, its orbital period, and its close proximity to a star whose output resembles our own Sun's places it among the most straightforward cases for lava world classification. What makes HD2 13885b observationally significant is the brightness of its host star. A brighter star is easier to study in detail. The starlight that passes through or reflects from a planet's atmosphere and the thermal emission that comes from the planet itself are both measured as fractions of the host star's total light output. The brighter the star, the more photons arrive at any given telescope within any given observing window, and the more precisely any planetary signal within that light can be measured. Ecto-C2 13885b's host star, by virtue of resembling the Sun in output, is among the more favorable targets for precise characterization of whatever atmosphere or surface emission the planet produces. In the catalog of lava world candidates, it sits at an intersection of the scientifically accessible and the physically extreme. A Sun-like star seen from the surface of a planet orbiting it at 1/100th of the Earth-Sun distance would not appear as a disk in the sky. It would occupy roughly 10 degrees of arc, a span 30 times the apparent width of the Moon as seen from Earth. There would be no sky left in any meaningful sense above the sunward point. The star's light would fill the entire upper hemisphere of the planet's dayside with an intensity that makes any comparison to sunlight on Earth inadequate. Sunlight on Earth is warm and yellow and falls at an angle that changes through the day and year. The light arriving at HD2 13885b's dayside is a sustained, direct, concentrated radiation that does not vary, does not angle, does not soften, and does not stop. It arrives at the same intensity at the same point of the sky for as long as the planet exists and the star burns. Below that light, on a surface made not of continent or ocean floor, but of slowly flowing molten silicate rock, the energy is absorbed, redistributed by the motion of the melt, and partially radiated back outward. The planet glows. Not like a star, its temperatures are far below the conditions of nuclear fusion, and the light it emits is thermal radiation from its surface, rather than light generated in a core. But it glows nonetheless, and that glow is measurable. The instruments that detect lava worlds can, under the right observing conditions, pick out the difference between the planet's thermal brightness on its day side and the relative darkness of its night side as it moves through its orbital phases. That difference tells astronomers how efficiently the planet moves heat from its sunward face to its dark one. A large difference means the heat stays concentrated on the day side, suggesting little atmospheric or magmatic redistribution. A smaller difference suggests heat is being moved by winds or by the slow lateral flow of the magma ocean itself. Each of these named worlds, 55 Congree O, Kepler 10b, Corot 7b, K2 141b, HD 213885b, was found by the same essential method, and each was found by the same essential evidence, the brief, repeating dimming of starlight as the planet crossed its star's face. The method is elegant in a quiet way. It requires no imaging, no direct detection of reflected light, no spectroscopic color measurement at the moment of discovery. It requires only that the planet's orbital plane be aligned closely enough with the line of sight between the star and the observer that the planet passes in front of the star rather than above or below it. Most planets around most stars do not produce transits visible from Earth, simply because orbital planes are distributed in all orientations and only a small fraction happen to align correctly. The ones that do produce transits are, in that sense, the ones that were already positioned to be found, not the most common lava worlds, but the ones whose geometry made them accessible from here. This means the catalog of known lava world candidates is in all likelihood a narrow sample of a much larger population. The galaxy contains hundreds of billions of stars. The fraction of Sun-like stars with close orbiting rocky planets is not known precisely, but surveys suggest it is not negligible, perhaps a few percent, perhaps more, with significant uncertainty. Among the red dwarf stars that make up the majority of stars in the galaxy, close orbiting rocky planets appear to be quite common. If even a small fraction of those close orbiting rocky planets have dayside temperatures above the silicate melting threshold, the count of lava worlds in the galaxy alone could number in the millions or more. The 5 worlds named here are not a complete picture. They are a first few words of a very long list. Kepler 10b orbits at a distance where the star's light arrives with roughly 1,500 times the intensity that sunlight arrives at Earth. Corot 7b, at its orbital distance, receives stellar radiation at a level that warms its day side to temperatures that exceed the boiling point of most metals. K2 141b receives stellar radiation so intense that the common rock-forming minerals arrive not as radiation, but as a sustained, direct energy flux, sufficient to drive the surface above the boiling point of rock itself. These are not gradations of a single phenomenon, but a spectrum, a range of extremes along which lava worlds occupy different positions, with different surface chemistries, different atmospheric compositions, different wind regimes, and different rates of atmospheric loss. What they share is the magma ocean. What distinguishes them is everything above it. The thermal emission phase curve of a lava world carries within it the information about how that ocean and its overlying atmosphere interact. As the planet moves through its orbit, from the position where its day side faces the observer to the position where its night side faces the observer, and back, the total thermal brightness measured from Earth follows a curve. The shape of that curve encodes how much heat is concentrated on the day side, how much has been transported toward the terminator and night side, and how rapidly the thermal profile changes across the planet's surface. For 55 Cancri, the shape of that curve has been measured, and it shows an asymmetry. The hottest point on the planet is not directly below the substellar point, the point where the star sits directly overhead, but is shifted in the direction of the planet's orbital motion. This shift is not an artifact, it is a physical signal suggesting that something atmospheric wins, or the flow of the magma ocean, or both is carrying heat slightly ahead of where simple geometric heating would concentrate it. The substellar point of a lava world is the location on the planet's surface that faces the star directly. At that point, the star is directly overhead, and the stellar flux is at its maximum. On 55 Cancri, this point has remained in the same position for as long as the tidal lock has held, receiving the same total solar energy input for millions of years. Over that time, the molten rock beneath it has been continuously heated from above and continuously replenished from below by convection rising from the deeper magma. Whatever crust-forming processes might operate at lower temperatures, the thin solidified skin that forms when lava cools at a terrestrial volcanic field cannot operate here. The incoming radiation exceeds the rate at which any thin crust could form and persist. The substellar surface of 55 Cancri is, to the best of current understanding, permanently, continuously open molten rock. The light from all 5 of these planets has been measured in various ways by telescopes in orbit and on the ground. None of these worlds has been visited. None has been seen in any image that shows surface features. They exist in the scientific record as light curves, radial velocity measurements, thermal emission spectra, and phase curves as patterns in data reduced from photons that traveled for decades or centuries before entering a detector. From those patterns, the models are built, and from the models, the surfaces are inferred. The confidence in the inference varies from planet to planet. For some, the rocky composition is well established by multiple independent measurements. For others, the surface temperature is constrained to a range, but not a precise value. The exact nature of whatever thin atmosphere any of them may carry remains, in most cases, a subject of ongoing study, not settled fact. What is settled is the category. These are rocky worlds in ultra-close orbits, with dayside temperatures that sustained silicate melting requires. The magma ocean is not a speculative feature, it is the expected physical state of a rocky surface under those conditions, as natural and as inevitable as ice forming on water at temperatures below freezing. The same physical chemistry that governs the behavior of rock in an Earth volcano governs the behavior of rock on a lava world surface. The temperatures are different. The scales are different. The persistence is absolute rather than temporary. But the underlying physics is the same physics that produced Kilauea's lava fields, Iceland's volcanic plains, and the basalt floors of every ocean on Earth. A lava world is not a geological impossibility. It is a geological certainty, given the right conditions, and those conditions exist. The star 55 Cancri is burning now, as it burns every moment, pouring radiation outward in all directions. At 1.5 hundredths of an astronomical unit, 55 Cancri is receiving its share of that radiation, as it has for billions of years, and its dayside surface is molten, as it has been for most of its history. The planet does not know it has been found. The ocean does not pause. The atmospheric vapor rising from the ocean's surface continues to rise, as it does every moment, not because anything has disturbed it, but because the temperatures make it inevitable. 41 light years away on a small rocky planet that also has a molten interior, though its surface cooled long ago to a thin, stable crust. Instruments recorded the dimming of a star. The recording went into a database. People read it. The numbers made sense in a specific way. And a world that no human will ever stand on. A world whose surface would vaporize any matter known to biology within moments, was added to a list of places that exist in the universe and have been, in the only way currently possible, found. The transit that revealed K2-141b lasted a matter of hours. The light dipped, held, and recovered, and in that recovery was the full outline of a world orbiting at 6.7 hours, with a day side at 3000 Kelvin, with silicate rain falling on a surface that has never seen the star it orbits. The light recovered, and the star continued, and the planet continued around it, and the cycle of evaporation and precipitation and deposition continued as well, unhurried and regular and indifferent to the instruments that had caught, from a great distance, its quiet signature in the brightness of a distant star. HD 213885 re-orbits a star that from Earth resembles the Sun in color, in temperature, in the warm yellow quality of its output. Seen from a very great distance, the system would look almost familiar. A sun-like star with a planet close in. The details at that distance would be invisible. The planet's proximity, the magma ocean on its day side, the permanent noon that has lasted for the length of the planet's history, none of it would be apparent. Only when the data was collected and processed, the brightness of the star monitored for months, the radial velocity wobble measured with great care, did the details emerge from the signal. A rocky world close in, hot enough to melt, a lava world around a sun-like star in a system that does not look from a distance so different from our own. Among the things the transit method has established is that lava worlds are not confined to exotic stellar environments. They do not require unusual stars, ancient stellar populations, or rare elemental abundances. They occur around red dwarfs, as K2-141b demonstrates. They occur around stars older and cooler than average, and they occur around stars like the Sun, as HD 213885b demonstrates. Stars with roughly the same mass, the same temperature, the same broad characteristics as the star that warms the Earth each morning. The conditions that produce a lava world are simply an orbital distance short enough and a stellar luminosity sufficient to raise a rocky surface above the silicate melting threshold and hold it there. Those conditions are not rare. They require only that a rocky planet form or migrate into a close orbit. In a galaxy of hundreds of billions of stars, most of them orbited by planets, close orbiting rocky worlds appear with enough regularity that the catalog of lava world candidates has grown steadily with each new telescope and each new survey. That catalog is still growing. The worlds named here were found first, and they carry the character of first discoveries, somewhat imprecise in their characterization, surrounded by questions that subsequent observations are slowly resolving. Future observations, with telescopes of greater sensitivity and broader spectral range, will measure the thermal emission of more lava worlds with greater precision, constrain the composition of their atmospheres, or the lack thereof, and map the thermal gradients across their surfaces with enough resolution to distinguish between models that predict very different physical regimes. The science of lava worlds is not finished. It is early. The named worlds are the first chapters of a catalog that the physics of planet formation suggests will eventually contain a great many entries. The star of 55 Cancri, visible tonight without optical aid in the constellation Cancer, continues to shine. Within its system, too small and too close to separate from the star's own light by any telescope currently operating, the planet 55 Cancri moves along its 18-hour orbit. The magma ocean on its sunward face receives the same radiation it has received for billions of years. Above the ocean, if the James Webb observations are correctly interpreted, a thin atmosphere of volatile compounds holds for now, though how long it persists against the stellar wind and ultraviolet radiation is an open question that the data so far does not resolve. Below the ocean, tarsens verret the Pequot's Ewing. Below the oceans of what's late Darn Bronstaf, the planet's interior, warmed by the decay of radioactive isotopes and the residual heat of its formation, adds its contribution to the thermal budget, though the stellar irradiation so overwhelms the interior heat source that the planet's deep interior is a secondary consideration for the surface conditions. The ocean moves, not dramatically, not with waves or tides in the familiar terrestrial sense, though tidal forces from the star do act on the planet and may produce some degree of internal stress and deformation. It moves as a fluid responds to thermal gradients, with hotter and slightly less dense material rising and cooler and denser material descending, the whole body of the ocean slowly circulating, carrying heat from depth to surface and from the substellar region toward the terminator. That circulation is a kind of weather. It is not spectacular in any visual sense. The surface of the ocean, seen from above, would appear to a hypothetical observer as a slowly shifting, glowing expanse. Not much different from one moment to the next. The large-scale currents invisible against the background of the ocean's own thermal emission. But over millions of years, that circulation shapes the chemistry of the ocean, moves material from one part of the planet to another, and may affect the composition of whatever vapor rises above it into the thin atmosphere above. The ocean is not passive. It is a slowly but continuously active body, responding to the energy it receives and radiating away what it can, maintaining its liquid state in a balance that the physics of stellar irradiation makes permanent for as long as the star continues to shine at its current luminosity. The balance is not delicate in the way biological systems are delicate. It is robust, maintained by forces that operate on planetary scales and are not perturbed by anything short of a change in the star itself or a major orbital disruption. The 5 worlds considered here: 55 Cancri, Kepler 10b, Corot 7b, K2 141b, HD 213885b, are among the best characterized examples of a type of planet that exists throughout the galaxy. They were found by patient observation, by instruments designed to detect the faintest possible signals, and by the accumulated work of many people over many years working with data that is, in the end, simply the precise measurement of how much starlight arrives at a detector at each moment of the observing night. From that data, planets were inferred. From the planets, temperatures were estimated. From the temperatures, surfaces were modeled. From the surfaces, a class of world was defined. And from the class, a population, many more, uncounted, unnamed, orbiting their stars in their short years, their dayside oceans flowing in the permanent noon of their locked orbits, their night sides cold and dark and receiving whatever falls from the thin sky above. The light from HD 213885b's host star crossed the distance between that system and ours over many decades before entering any instrument. When it arrived, it carried within it, encoded in the precise regularity of its brightness and the subtle wobble of its spectrum, the evidence of a planet of rock and iron, a planet orbiting in one day, a planet whose surface, on the side that always faces its star, is not stone in any solid sense, but a slowly flowing ocean of mineral melt, glowing at temperatures that would, from a safe distance, appear as a faint, warm radiance wrapped around one hemisphere of a dark world, the other hemisphere cold and unreachable and silent, the two halves of a single world separated by a boundary as absolute as any in nature, the permanent line between the face that burns and the face that does not, drawn in geological time and held there without variation, while the star goes on shining and the orbit continues and the slow, ancient ocean of rock flows on below. From the surface of a lava world's magma ocean, stone does not sit still. It breathes, not in the way a chest rises and falls, not in the way a tide pulls back from a shore, but in a slower and more continuous way, a ceaseless, quiet release of mineral vapor rising from the surface of the melt into the thin air above, a planet exhaling its own substance into the sky, one molecule at a time, without pause, without urgency, in a process that has continued for as long as the magma has been liquid and the star has been close. The surface temperature at the center of the dayside is high enough that the boundary between rock and air is not fixed. On Earth, that boundary is absolute. Stone is stone, air is air. The line between them does not move, does not blur, does not dissolve. Here, the line is a gradient. The uppermost layer of the magma ocean shades continuously from liquid rock to a thin atmosphere of the same elements, only in their gaseous form: silicon, magnesium, iron, oxygen, sodium, potassium, all lifted free of their mineral bonds by heat alone, all drifting upward into a sky that is, in its composition, a kind of airborne geology. The air above the magma ocean is made of the same material as the ocean below it. Only the temperature separating them decides which is which. That thin sky carries no nitrogen, no oxygen in the breathable sense, no carbon dioxide, no water vapor. None of those gases belong here. What the atmosphere holds instead are the vapors of minerals that on any cooler world are locked permanently into the crystalline structures of rock, into pyroxene and olivine and feldspar, into the slow, dense architecture of geological stone. At temperatures that would vaporize steel, those structures cannot hold. The bonds that keep silicon and oxygen and magnesium arranged in orderly lattices give way under the pressure of the heat, and what had been rock disperses upward as gas, as fine invisible vapor, carried away from the surface on the same thermal currents that stir the upper layers of the melt. This is the first layer of a lava world's atmosphere, not a thin film of familiar gases, not a preserved remnant of some earlier cooler state. It is an atmosphere generated fresh, continuously, by the evaporation of the surface beneath it, replenished as fast as it is lost, sustained not by some ancient reservoir, but by the ongoing process of a whole world slowly giving itself to the sky. The magma ocean evaporates slowly, evenly, across the breadth of the dayside. The vapor rises, and because the planet is tidally locked, it has nowhere to rise to that is not also caught in the same relentless starlight. The entire sunward hemisphere is illuminated at once, always, and the air above it is everywhere warm and thin and rising, but atmosphere in motion does not stop at the sunward pole. It cannot. The pressure difference between the dayside, where the magma is boiling its gases upward and filling the sky with mineral vapor, and the night side, where no equivalent source exists, and the temperature drops away into a different geological world entirely. That difference is enough to set the whole atmosphere into motion. The gas does not stay where it is made, it moves. On Earth, the word wind calls to mind something familiar, a pressure on the skin, a sound in the trees, a thing measured in miles per hour and named by the direction it comes from. On a lava world, the word wind refers to something of a different order entirely. Modeling work done on the dynamics of planets like K2 141b, a world whose dayside reaches roughly 3000 Kelvin, a temperature at which rock becomes vapor, estimates that the atmospheric winds moving from the dayside to the nightside may travel at several kilometers per second, not several kilometers per hour, per second, fast enough that the entire atmosphere, from the point of its hottest generation above the magma ocean to the cold quiet of the night side, makes the crossing in a matter of hours. Fast enough to carry with it not just heat, but the chemical species that give the atmosphere its identity, transporting sodium and silicon monoxide and silicon dioxide like a river carries silt in bulk, continuously, without stopping. The image of a river is not quite right for what moves in these winds, because a river moves horizontally through a stable medium, while the wind of a lava world is the medium itself, the entire atmospheric column in motion, driven by a thermal gradient so steep that the word gradient almost fails to capture it. The day side and the night side of a tidally locked lava world are not merely different in temperature, the way a sunny side of a hill differs from the shaded one. They are different in temperature, the way the interior of a furnace differs from the open air of a winter night. The pressure that difference generates is not a gentle gradient. It is a sustained, enormous atmospheric imbalance, and the wind it drives is the planet's only mechanism for resolving it. The vapor carries outward from the day side in this fast, invisible current, silicon and magnesium, and the oxides of metals, all in their gaseous forms, all suspended in a thin moving sky, all traveling together toward the dark side of the world. And as they travel, as the distance from the magma ocean grows and the star falls lower in the sky and then below the horizon entirely, the temperature begins to drop. The drop is not gradual in the way a summer evening cools. It is a sharp descent from the heights of a molten world into the silence of a hemisphere that receives no light from its star at all. Cooling air cannot hold as much vapor as warm air. On Earth, this principle gives rise to clouds and rain. Water vapor that has risen from warm surfaces cools at altitude, condenses into droplets, and falls back to the ground. On a lava world, the same principle operates, only the vapor is not water, and the droplets are not rain in any familiar sense. As the mineral gases carried from the dayside atmosphere encounter the colder air of the night side, they begin to condense. Silicon monoxide becomes liquid. Silicon compounds begin to form tiny suspended particles, not the familiar gray-white of water clouds, but something glassy and dense, composed of materials that on Earth are found in volcanic rock and in the deep interior of mountains. These particles gather, they aggregate, they grow heavy enough that the thin atmosphere can no longer suspend them, and then they fall. The night side of a lava world in the best current models receives a kind of precipitation, not snow, not ice, a slow, fine, continuous rain of liquid silicate droplets, falling from a mineral sky onto a surface that may itself already be layered with the deposits of earlier falls. The droplets are not large, the atmosphere is too thin, and the condensation too fine for heavy drops, but they are steady. They fall across the dark hemisphere in a continuous, unhurried mineral drizzle, coating the surface in thin successive layers of cooled and solidified rock, not volcanic rock in the way that word is usually meant, because there is no eruption, no vent, no explosive release of pressure, just a slow, accumulated settling, stone falling gently out of the sky. This cycle, evaporation from the dayside magma ocean, atmospheric transport across the terminator, condensation and precipitation on the night side, is one of the most striking features of a lava world's global dynamics. It resembles, in its logic and its geometry, the water cycle of Earth. There is a source region where a fluid evaporates. There is atmospheric transport. There is a cooler receiving region where the vapor condenses and falls. There is, presumably, a return flow of some kind, the accumulated material of the night side eventually finding its way back toward the heat of the day side through the slow motion of the magma ocean or through geological recycling. The cycle is continuous. The materials are different. The temperatures are higher by more than 1,000 degrees. But the underlying logic, heat drives evaporation, transport carries the vapor, cooling produces precipitation, gravity returns the material to the surface, is the same. What falls on the night side of a lava world builds up over time. The deposits are not uniform. The coldest, most sheltered zones, far from the terminator, receive the most accumulation, closer to the boundary between light and dark, where temperatures are transitional and the atmosphere is still partially warm. The condensation is less complete. The edge of the night side is a zone of incomplete precipitation, of partially condensed particles, of droplets too warm to fully solidify before they reach the surface. Farther in the deep cold of the permanently unlit hemisphere, the precipitation is more thorough. The surface there may be layered in ways that reflect the history of the atmosphere, thin beds of mineral deposits, each representing a long period of steady fall, recording in their thickness and composition the conditions of a sky that no instrument has yet directly sampled. The atmosphere above the night side is not empty, even in the coldest regions. It holds the residue of what the wind carried and what the condensation left behind. Thin, cold, mostly stripped of its most volatile components, but still present. And even here, the atmosphere is not static. The winds do not stop at the point of condensation. They continue, driven by the same pressure gradient that set them moving until the gas has distributed itself across the whole dark hemisphere and the pressure has equalized enough for the flow to slow. Below the path of these winds, the surface records what passed overhead. There is a second kind of cloud formation that the models propose for these worlds, distinct from the low-altitude condensation that produces silicate rain. Higher in the atmosphere, in regions where the temperature is lower still, the silicate and metal oxide vapors that have not yet fully condensed can form suspended clouds of tiny crystalline or glassy particles, mineral aerosols, drifting in the upper sky. These are not soft and diffuse like cirrus clouds seen against a blue sky on Earth. They are composed of particles of magnesium silicate, of iron oxide, of corundum, an aluminum oxide mineral that on Earth produces rubies and sapphires when trace elements color its transparent crystal structure. In the upper atmosphere of a lava world, corundum forms as a fine, hard mineral dust suspended far above the surface, invisible from below, but capable of affecting how the planet absorbs and re-emits the light of its star. The optical properties of these mineral clouds matter enormously for the study of lava worlds from afar. A cloud layer composed of glassy silicate particles reflects some fraction of incoming starlight back into space, reducing the amount of energy the planet absorbs. A layer rich in iron oxides may absorb certain wavelengths of light, preferentially, shifting the balance of heating across different atmospheric altitudes. The clouds are not decorative. They are active participants in the planet's energy budget, altering the temperature structure of the atmosphere and, by extension, the conditions at the surface. They also alter what telescopes on Earth or in orbit can detect, since the signal that travels across light years to reach an instrument carries the imprint of whatever the light passed through on its way out of the planet's atmosphere. The clouds, the winds, the silicate rain cycle, all of these operate within the atmosphere, but the atmosphere itself is not permanent. It is under pressure from above, as well as below. The star whose heat sustains the magma ocean and drives the evaporation that feeds the atmosphere is also the star whose radiation slowly destroys it. High energy radiation, ultraviolet light, and X rays carries enough energy to break molecular bonds and heat gas to the point where the planet's gravity can no longer hold it. Gas in the upper atmosphere of a lava world absorbs this radiation, heats rapidly, and in a fraction of the time it takes the lower atmosphere to cycle through its silicate rain pattern, rises high enough to be caught by the stellar wind, the continuous outflow of charged particles that streams from every active star. Once caught by the stellar wind, the gas is swept away into space. It does not return. The process is called photoevaporation, and it operates on a lava world continuously and at a steady rate, removing material from the top of the atmosphere as fast or faster than the magma ocean below can replace it. The two processes, upward supply from the evaporating surface and upward loss to the stellar wind, are not necessarily in balance. For some lava worlds, in some orbital configurations, the supply rate from the magma ocean may exceed the escape rate from photoevaporation, maintaining a persistent atmospheric layer in a dynamic but stable state. For others, especially worlds in very close orbits around young active stars that emit more high-energy radiation, the escape rate may exceed the supply, and the atmosphere may thin steadily over geological time. The most volatile components, sodium and potassium, which vaporize most easily and sit highest in the atmosphere, where they are most exposed to stellar radiation, leave first. What remains, as the atmosphere ages and thins, is an increasingly impoverished mixture dominated by the least volatile silicate components, silicon dioxide, magnesium oxide, the residue of a once richer sky, still present but simpler, harder, stripped of its more mobile elements by the patient pressure of the star. This stripping does not happen quickly. Geological timescales measure these processes in millions of years, even hundreds of millions of years. A lava world whose atmosphere has been losing its sodium for 100 million years does not look dramatically different from one that has only recently begun the process. The difference is chemical rather than visible, a shift in the relative proportions of gaseous species that only the most sensitive spectrographs can detect. But the direction of change is always the same, from rich and varied and chemically active towards simpler and more residual and less dynamic. The planet does not fight this change. Nothing fights it. The atmosphere simply ages, component by component, at the pace set by the star. There is something contemplative in the image of that slow stripping, not a dramatic loss, not a sudden event, just the quiet removal, year by year and eon by eon, of one element after another from a sky that was once full of them, leaving behind the stubborn, the hard, the non-volatile, the last mineral vapors clinging to a world that has been giving itself to space for longer than the Earth has existed in its current form. The least volatile silicate components, the ones that persist longest, are also the ones most deeply embedded in the mineral lattice, silicon dioxide in particular, the primary component of quartz and many common rock-forming minerals. In vapor form, Above a magma ocean at several thousand Kelvin, silicon dioxide is not the familiar, colorless, transparent material found in beach sand and window glass. It is a reactive gas, a component of a sky that no element in the natural world on Earth has ever had to breathe. But it is stable enough to persist after sodium and potassium and the more volatile metals have been carried off by the stellar wind. It is, in a sense, the last thing standing. Above this aging atmosphere, far out in the thin transition between the planet's gravitational hold and the open flow of the stellar wind, there is a region where the gas becomes unconstrained. The distinction between atmosphere and space blurs. Individual atoms and molecules follow ballistic trajectories rather than fluid flow, rising on thermal energy alone, slowing as gravity pulls them back, and sometimes, when they are moving fast enough, or when a burst of stellar radiation gives them an extra push, escaping altogether. This diffuse, unconfined outermost layer of a planetary atmosphere is called the exosphere. On Earth, it extends for thousands of miles above the surface and is so thin it barely qualifies as an atmosphere at all. On a lava world, the exosphere is not thin in the same way because the supply of material from below is continuous and enormous. The boundary between the planet and the space around it is permeable and has been permeable for the entire life of the lava world. Over that whole time, the lava world has been releasing itself into space, not rapidly, not catastrophically, but steadily at the rate that the balance of evaporation and escape permits, depositing a faint trail of mineral atoms in the space surrounding its orbit, a kind of chemical signature of the planet written in the empty space through which it travels. This trail is not observable with any current instrument. It is too diffuse, too mixed with the material of the stellar wind, too scattered by the time it reaches any detectable concentration. But it is there in principle, the long, slow exhalation of a world that has been breathing out for billions of years, leaving its elements distributed along its orbital path like a comet's tail made of silicate vapor, quiet and invisible and real. The silicate rain cycle continues on the night side throughout all of this. While the upper atmosphere erodes, the lower atmosphere maintains its circulation. The winds move, the droplets fall, the deposits accumulate. The surface of the night side receives its mineral precipitation, as it has always received it, layer by layer, in the cold and the dark, at a rate too slow to observe directly, but too persistent, over deep time, to leave no trace. The mineral deposits on the night side are not static once they have settled. The lava world is not a cold, inert place on its dark hemisphere. It is merely cooler than the day side, and cooler on a lava world still means temperatures that would be extraordinary by any terrestrial standard. At the terminator, the boundary where night and day meet, temperatures may cross the solidification point of silicate rock, meaning that the surface near the boundary transitions from liquid to solid, or solid to liquid, depending on slight variations in local energy balance. Material that condenses and falls near the terminator may remelt when it lands, adding to the magma ocean rather than forming a stable deposit. Material that falls farther into the cold of the night side solidifies as it hits the surface and stays solid, building up over time. This boundary zone, where falling mineral precipitation meets the edge of the magma ocean, is one of the most physically active regions on a lava world. It is where the rain cycle terminates. It is where the chemistry of the night side intersects with the fluid dynamics of the dayside magma. It is where temperature gradients are steepest, where the phase of silicate rock shifts from liquid to solid over a horizontal distance that may be measured in hundreds of miles. And it is where the return flow of material, The slow recycling of nightside deposits back toward the hot dayside begins, driven by the gradual motion of rock across the terminator and by the deep circulation of the magma ocean beneath. The cycle is closed, not perfectly, not without loss. The ongoing photoevaporation means that some fraction of what evaporates from the dayside is lost to space rather than precipitated onto the night side, but materially closed enough that the process has continued for the whole geological life of the planet. The atmosphere is replenished from the ocean. The ocean is fed in part by the precipitation. The precipitation is generated by the wind. The wind is driven by the heat. The heat comes from the star. The star has been shining over this world for billions of years, driving the same cycle in the same direction with the same relentless pressure and the same patient outcome. What changes over those billions of years is the chemistry. The sodium leaves, the potassium follows. The more complex volatile mineral species simplify. What remains is older, harder, less dynamic in its chemistry, even as it continues to move in its physics. The atmosphere above an ancient lava world may be quieter in its reactions than the atmosphere above a young one, but the winds still move. The silicate rain still falls. The mineral clouds still drift in the upper sky, scattering the starlight that has been falling on this world since before the Earth existed, or since before whatever star this planet orbits had cooled enough to burn steadily. The glassy particles of those high-altitude mineral clouds catch the light of the star and scatter it in all directions, a faint haze of mineral optics that alters the color and brightness of the planet as seen from far away. To a distant observer, to a telescope pointed at this star from across tens of light years, the lava world appears as a tiny variation in light, a dip in brightness as it crosses the star's face, a shift in the spectrum of light reflected from its atmosphere, carrying the chemical fingerprints of silicon and magnesium and the other mineral vapors suspended in its sky. The planet does not announce itself. It is detected through patience, through precision, through the accumulation of many measurements over many transits. But in the spectrum of that faint, distant light, the atmosphere speaks. The wavelengths absorbed by sodium vapor leave a gap in the spectrum at a precisely known position. Silicon monoxide and silicon dioxide have their own spectral signatures, slightly different in position and depth. Magnesium vapor absorbs at its own characteristic wavelength. Each chemical species leaves its mark in the outgoing light of the planet, a set of narrow dark lines against the broader glow, each one pointing to an element present in the sky of a world that no instrument has ever been close to, that no probe has ever entered, that exists at a distance measured in the time it takes light to travel for decades or centuries. Those spectral lines are the atmosphere's voice. They do not speak clearly, and reading them requires years of observation and careful subtraction of noise from signal. But they are there, and they carry real information about what moves in the winds above a magma ocean, several thousand Kelvin hot, on a planet completing its orbit in a matter of hours, around a star that it will never leave, and that it has been orbiting since the solar system that contains it first condensed from its primordial disk. The winds slow as the gas approaches the center of the dark hemisphere. Far from the terminator, the driving pressure gradient is reduced. The gas has already traveled across most of the night side, giving up its heat and much of its chemical content to the air below, and the wind that was supersonic near the boundary has quieted to something more subdued. The particles falling here fall through air that is nearly still. The silicate droplets descend in quiet, widely spaced trajectories, each one a small cooling bead of liquid mineral, suspended briefly between the sky and the surface, before gravity closes the distance. There is no sound. There is no light. In the deep night side, far enough from the terminator that even the faint glow of the magma ocean's edge is below the horizon, the sky is dark. Whatever stars are visible from here are not familiar. The host star has set below the horizon and does not rise, and the sky above is a different hemisphere of stars than the one that the dayside sky faces, turned permanently away from the brightness. In this direction, the galaxy continues in its faint band across the dark. The mineral particles fall. The surface below them receives another thin layer of accumulated silicate, another increment in the geological record of a world that has been writing the same slow record for longer than memory extends. The atmosphere, for all its alien composition and all the violence of its supersonic winds at the terminator zone, settles here into something almost quiet. Not peaceful in the way a landscape can be peaceful. There is no life here, no water, no gentleness of surface, but quiet in the physical sense of low energy, low motion, low sound, low light. The storms, if they can be called that, are on the other side of the world. The heat, the evaporation, the enormous pressure of the star bearing down on the molten surface, all of that is elsewhere. Here, the mineral rain falls into stillness. Over geological timescales, those thin layers of mineral rain accumulate into something more substantial. Not mountains, not plains in the earthly sense. The world is too hot at depth, too close to its star, too physically active at the terminator for stable geological structures to persist in the way they do on a cold, quiet world. But somewhere between the terminator and the deep night side, there may be a region where the surface is solid, where the silicate deposits of many millions of years of precipitation have built a thin crust of layered stone, each layer a record of a different period in the atmosphere's chemical history. The older, richer layers below, the simpler, more stripped layers above, the whole sequence sealed by the continued fall of the present. The topmost layer of that record is still forming now. The newest precipitation is landing even now on a surface that it has never touched before, adding its thin increment to the history of a world in motion, a world generating its own geology from its own sky, a world that has been slowly and continuously writing itself onto its own dark face for as long as the star has been burning and the orbit has been tight and the magma ocean has been giving up its vapors to the air. The vapor rises from the bright side. The wind carries it across. The clouds form in the cold upper air. The rain falls in the dark. The surface receives it, and the star continues to shine, and the atmosphere continues to thin, and the sodium that was once abundant in the sky of this world is now scattered somewhere in the stellar wind, dispersed into the interplanetary medium, part of the wider chemistry of the system, gone from the planet that made it, but not gone from the space around it, just more diffuse, more distant, more free. What remains of the atmosphere above an old lava world is still an atmosphere, still moving, still fed from below by the evaporating magma ocean, still carrying the last of the mineral vapors in its thin currents from the bright side to the dark. The cycle does not stop because it has lost some of its participants. It continues with what it has. Silicon dioxide vapor rises from the magma. The wind catches it. The cloud forms in the upper sky. The droplet falls in the dark. The layer settles on the surface. It has always been this way. It will continue to be this way for as long as the star holds its brightness, and the orbit holds its closeness, and the planet holds its mass against the slow erosion of a billion years of stellar wind. The atmosphere will thin. The chemistry will simplify. The night side deposits will thicken in some places and thin in others as the circulation slowly shifts with the changing composition of the vapor. And through all of it, the wind will move, steady, fast, continuous, carrying stone through the sky from one side of a world to the other, depositing it in the cold and the dark, building a slow, layered record of a planet's long and patient surrender to the star that made it molten. The mineral clouds drift in the upper atmosphere. They have been drifting for longer than the Earth has had an ocean. The glassy particles of magnesium silicate catch and scatter a sliver of the star's light, a faint brightness visible from very far away. The surface of a world exhaling its own substance into the sky, quietly, continuously, without end. Molten rock at lava world temperatures does not move the way lava moves on Earth. On Earth, volcanic lava is thick and reluctant, heaping itself into slow ropes and crusted mounds, piling up around the edges of a vent as though unsure whether to spread or to stop. At 2500 Kelvin, that same material, the silicate minerals common to every rocky planet's outer layer, becomes something else. It thins, it flows. In the deep magma oceans of the worlds that orbit closest to their stars, the molten rock moves with a fluidity that has more in common with warm oil than with the lava of a terrestrial volcano. And that single physical fact, viscosity, the quality of resistance to flow, is the one that changes everything about how a lava world behaves at its surface. Viscosity is not a dramatic property. It does not announce itself. It is simply the degree to which a fluid resists the motion of one layer past another, the difference between water and honey, between cold syrup and warm, between a rock that holds its shape and a rock that does not. At the surface temperatures of tidally locked planets in ultra-close orbits, the common silicate minerals, the olivines, the pyroxenes, the feldspars that form the crust and mantle of every rocky world in the solar system, reach a state of melt so complete that their internal molecular structures lose nearly all resistance to deformation. The magma ocean that covers a lava world's sunward face is not sluggish. It is a rapid, globally active fluid, constantly in motion, its surface moving in response to forces that operate across the entire planetary interior. The forces that move it are thermal. Heat is the engine of everything that happens in a magma ocean, and heat is not distributed evenly across a lava world's surface. The dayside hemisphere, locked in permanent, unbroken exposure to the host star, receives a continuous flux of radiation orders of magnitude greater than anything the Earth absorbs from the Sun. The nightside hemisphere, permanently turned away from the star into the unlit dark, receives none. Between these two faces, a temperature difference of several hundred degrees persists not as a temporary condition, but as a stable, structural feature of the planet's existence, as permanent as the orientation of its axis, as fixed as the timing of its orbit. That temperature gradient is the pressure that drives everything. Warm fluid rises, cool fluid sinks. These are among the most basic facts of physical behavior, and in a magma ocean at lava world temperatures, where viscosity is low and heat is abundant, they operate rapidly and at enormous scale. Beneath the bright surface of the dayside, where the temperature is highest and the melt is most complete, rock that has absorbed the star's radiation is fractionally less dense than the material around it, and it rises. At the surface it spreads, losing heat to the thin mineral atmosphere above, and then, cooler now, fractionally denser, it begins to descend. On Earth, this same process of convective circulation operates in the solid mantle, but so slowly, through rock so stiff and resistant to flow, that the largest overturning cells take hundreds of millions of years to complete a single cycle. In a fully molten magma ocean at lava world temperatures, the same structural process operates on a timescale that might be measured in years or in days. The interior of such a planet is not quiet. It is continuously rapidly turning over, carrying heat from depth to surface and back again in a cycle that has no rest. The rising material carries something more than heat. As it ascends from depth, the buoyant melt brings with it the chemical signature of the planet's interior, heavier elements mixed into the flow from far below, lighter silicates swept upward in the current, the whole chemical inventory of the rock in slow circulation. A magma ocean that remains fully molten for long periods does not settle into layers the way a cooling ocean eventually might. The continuous convective overturn disrupts the sorting that would otherwise separate the planet's constituents by density, keeping the deep interior in communication with the surface in a sustained chemically active exchange. The planet is not layered so much as it is mixed. Its interior is a conversation, not a filing system. The surface of the magma ocean, seen from directly above, would not look still. It would not look like a glassy lake, or even like the calm surface of a slow-moving river. In wide, gentle upwellings, slightly brighter and fractionally hotter than their surroundings, material from below would emerge and spread laterally across the surface in slow, broad sheets. At the edges of these upwellings, where the surface material has cooled slightly and become denser, it would descend again in long, narrow zones, not plunging violently, but sinking with a quiet, continuous patience, the way a current in a deep ocean descends without breaking the surface above. The pattern across the day side would be something like the surface of a sun, convective cells covering the whole face of the planet in a slowly shifting mosaic of slightly brighter centers and slightly cooler margins, the whole arrangement in constant, almost imperceptible motion. Imperceptible because the scale is vast. A convective cell that would span an entire ocean on Earth would be a modest feature on a lava world surface. The largest upwellings might extend across regions the size of continents, and their motion, though rapid by the standards of solid rock, would still be slow enough that no single movement could be easily tracked. The magma ocean breathes, it turns over, it carries heat from the interior to the surface in a slow, continuous exhalation that has lasted without interruption for as long as the planet has held this orbit. That is long enough. The heat carried upward by convection does not simply accumulate at the surface, it must go somewhere. Some portion of it radiates away as thermal emission, the dull continuous glow of incandescent rock, visible from space as infrared light, the same physical process that makes a heated piece of iron glow orange in the dark. Some portion of it passes into the thin mineral atmosphere overhead, warming the lower atmospheric layers and driving the circulation of gas from the day side toward the cooler night side. And some portion of it, in a process that is less well understood, may move laterally through the magma ocean itself, not through the atmosphere above, but through the fluid rock below, carried from the hotter day side toward the cooler night side in a slow subsurface current of molten material. That lateral flow is subtle to imagine. The magma ocean, like any fluid confined to the surface of a sphere, is not free to simply spill from one side to the other. It is constrained by the planet's gravity, by its rotation, even if rotation is very slow on a tidally locked world, and by the pressure differences that arise from the temperature gradient between hemispheres. Deep beneath the visible surface of the day side, where the melt is hottest and the pressure from above is greatest, material is pressed outward and downward. Toward the night side, where the surface is cooler and the rock begins to stiffen toward the solidus, the temperature at which liquid first begins to crystallize, There is a zone of slightly lower pressure, and the lateral current flows toward it. Cooler material descends on the night side, making room below. Hotter material from the day side fills that room, moving at depth across the interior in a slow current that completes a circuit across the whole planetary interior. The day side and the night side are connected, not just through the atmosphere overhead, but through the rock itself below. How efficiently this interior circulation redistributes heat between hemispheres is one of the questions that cannot yet be answered with certainty. The temperature difference that an observer would measure between the day side and night side of a tidally locked planet, expressed in the form of a thermal phase curve, a graph of the planet's total thermal emission as it moves through its orbit, carries information about where the heat goes and how well it is shared. A planet that keeps most of its heat on the day side, losing very little to the night side, would show a large temperature contrast and a phase curve with a sharp, deep minimum on the night side pass. A planet that efficiently redistributes its heat, whether through atmospheric flow or through magma ocean circulation, or through both, would show a smaller contrast, a shallower minimum, a more uniform brightness around the orbit. The difference between these outcomes, encoded in measurements made across light years, is a window into the physical conditions operating deep inside a world the size of a continent that no one has ever visited. The night side is where the physics becomes most delicate. Away from the direct irradiation of the host star, the surface of a lava world is not guaranteed to remain molten. The exact state of the night side, whether it is fully molten, partially solidified, or covered in a thin, fragile crust of crystallized silicate floating atop a still liquid interior, depends on the balance between the rate at which heat arrives from the day side and the rate at which the surface loses heat to the cold of space. At the temperatures that prevail far from the substellar point, somewhere in the range at which common silicates begin to crystallize, the night side surface is close to a boundary. Liquid rock and solid rock are separated here by a margin of degrees, and conditions that tip the balance one way or the other will determine whether a thin crust forms or whether the surface remains liquid all the way around. That boundary between liquid and solid has a name in geology. It is the solatus. On Earth, the solatus of peridotite, the rock that makes up most of the upper mantle, lies at temperatures around 1400 to 1500 Kelvin at surface pressures, though it shifts with depth and composition. On a lava world, where the magma ocean is composed of partially or fully vaporized silicates, chemically altered by millions of years of extreme heating and atmospheric loss, the solatus may fall at somewhat different temperatures depending on what the ocean is made of. But the concept is the same. There is a temperature at which the liquid wants to crystallize. Below it, solids form. Above it, they do not. And on the night side of a tidally locked lava world, the surface temperature may rest close enough to that boundary that the question of solid or liquid has no stable, permanent answer. Imagine standing, not standing, but being present in whatever form a temperature of several hundred degrees would allow at the edge of the night side, where the substellar hemisphere gives way to the dark. The surface underfoot, if it is a surface, shifts in character. Where the irradiation is strong and the magma ocean is fully molten, the ground is not ground at all, but a slowly moving fluid, dark orange-red, glowing from within, its surface textured by the gentle convective motion below. Moving away from the substellar point, the temperature falls. The glow deepens to red, and then to a color barely visible. At some distance, at the precise distance where the surface temperature crosses the solidus, the fluid begins to stiffen. The first crystals form. They are small, irregular, and unstable, rising to the surface and sinking again as the temperature fluctuates with the slow circulation of the magma below. But they persist, and as the temperature falls further, they multiply and thicken until the surface is no longer liquid, but a thin, irregular crust of dark crystallized rock floating on a still hot interior. This crust is fragile. It is not the stable, ancient continental rock of a geologically quiet world. It is newborn material, freshly crystallized from a melt still warm enough to remelt it at the slightest provocation. Where the interior circulation brings a pulse of hotter material toward the surface, the thin crust above it softens and sinks back into the melt. Where the surface loses heat more rapidly, where a slightly cooler region has formed, the crust thickens. It is a surface in a state of continuous, slow becoming, never fully solid, never entirely stable, advancing and retreating across the night side in response to a thermal balance that is always in motion. What lies beneath this crust or beneath the fully molten dayside surface, deeper into the planet's interior, involves a force that has nothing to do with heat or convection directly. The moving fluid of a magma ocean carries electrical charge, however faintly. Molten silicate rock, at the temperatures of a lava world's deep interior, can carry electric currents, and moving electric currents produce magnetic fields. On Earth, the magnetic field arises from convective motion in the liquid iron outer core, a fluid of high electrical conductivity moving in complex patterns, driven by the planet's rotation and the heat flux from the solid inner core below. A lava world with its deep, convecting magma ocean might generate a magnetic field by a related process, though the electrical conductivity of molten silicate is lower than that of liquid iron, and the field it could sustain would likely be weaker and more variable. A magnetic field would matter enormously. Stellar wind, the continuous stream of charged particles flowing outward from a host star at high velocity, is at the close orbital distances of lava worlds far more intense than the solar wind that presses against Earth's magnetosphere. Without a magnetic field to deflect this flow, the upper atmosphere of a lava world would be exposed to direct bombardment by energetic ions, stripping gas molecules away and accelerating the erosion of whatever thin mineral atmosphere sits above the magma ocean. With a field, some portion of the stellar wind would be deflected, bent away from the polar regions, guided along magnetic field lines to deposit its energy at the poles rather than across the whole upper atmosphere. The planet's ability to hold any atmosphere at all, even the thin, hot mineral vapor that rises continuously from the magma surface, would depend in part on whether the flowing rock below generates enough electromagnetic activity to build and sustain that invisible shield. Whether most lava worlds have magnetic fields, whether those fields are strong enough to matter, and how the fields vary over geological time as the composition and convective vigor of the magma ocean change. These are questions to which current observations provide only indirect and partial answers. The science here stands at an open boundary. The physics is clear in outline. A conducting fluid in motion can generate a magnetic field, and a lava world's magma ocean is a conducting fluid in motion. What is less clear is whether the conductivity is high enough, the convective velocity fast enough, and the field organized enough to sustain a coherent global magnetosphere against the intense pressure of close orbit stellar wind. No observation has yet settled this question. It remains an open door into the interior of a world that cannot be visited. The transition zone between the molten day side and the stiffening night side is not a line drawn cleanly across the planet's surface. Nothing at this scale is clean. The zone is wide and irregular, advancing and retreating as the interior circulation fluctuates, deepening toward the center of the night side and thinning toward the edges, its exact position at any moment a function of the heat flux arriving from below and the radiation being lost from above. Along this zone, the physical state of the surface rock passes through every intermediate condition between full melt and full solid, through a state that geologists call the mush zone, where the rock is neither entirely liquid nor entirely solid, but a mixture of both, a suspension of growing crystals in a still liquid residue. In the mush zone, the behavior of the rock is unlike either of its end states. Fully molten rock flows easily, obeying the simple physics of a low viscosity fluid. Fully solid rock holds its shape against any force short of fracture. Mush does neither. It is a material that can be deformed under sufficient force, but that retains some memory of its shape, that flows slowly if pushed, but does not rush to fill a void, that transmits pressure in ways that depend on how many crystals it contains and how they are arranged. On Earth, mush zones exist beneath active volcanoes, where partially crystallized magma sits in subsurface reservoirs waiting for a trigger to erupt. On a lava world, the mush zone exists not in a local reservoir, but as a planetary scale feature, a band of uncertain matter encircling the globe, the physical expression of the temperature gradient between the star-facing hemisphere and the dark one. In the mush zone, crystals form and dissolve on timescales that vary with local conditions. Where a pulse of hotter material arrives from depth, the crystals soften and the mush becomes more liquid. Where the surface above loses heat rapidly, the crystals grow and the mush stiffens. Denser crystals sink through the liquid fraction, lighter residual melt rises. The zone is in constant internal redistribution, sorting and resorting its constituents in a slow, continuous process that, given enough time, would organize the planet's interior into distinct chemical layers. But on a lava world, the convective overturn may operate fast enough to disrupt this sorting almost as quickly as it occurs, maintaining a chemical composition in the mush zone that reflects the well-mixed interior of the planet rather than the settled product of slow differentiation. The planet breathes through all of this, not metaphorically, but physically. The interior convection, the lateral flow between hemispheres, the mush zone advancing and retreating, the crust forming and remelting on the night side, the mineral vapor rising and condensing and falling. All of this constitutes a continuous planet-wide exchange of matter and energy that has no analog anywhere in the current solar system and no precedent in any world that has been visited or sampled or drilled. A lava world is not a rock. It is not a volcano. It is not a body of water. It is a kind of planet that exists only at the extreme, close margin of stellar influence, where the ordinary categories of geology dissolve as completely as the minerals that make them up. Deep within the dayside hemisphere, beneath the surface convection, beneath the layer of active upwellings and descending currents, the magma ocean extends to great depth. How deep depends on the planet's mass and composition. For a planet roughly twice the size of Earth, a super-Earth, as the category is described, though the qualifier carries almost no weight when the surface is this different. The magma ocean may extend through tens or hundreds of kilometers of depth before encountering a transition to rock under such enormous pressure that the increased pressure raises the melting point, and the rock becomes solid again, even at temperatures that would melt it at the surface. This region, a solid interior under pressure, surrounded by a liquid outer layer under stellar irradiation, mirrors, in broad structural terms, the internal arrangement of Earth itself, where a liquid outer core surrounds a solid inner core. The analogy is imperfect, and the scales are different, but the physics that creates both situations is the same. Pressure, like heat, controls the state of matter, and at sufficient depth, even the hottest planetary interiors freeze. The pressure at depth compresses the rock. Crystal structures that are open and loosely packed at the surface are rearranged under the weight of kilometers of overlying material into denser, more compact forms, high pressure mineral phases with no surface equivalent. On Earth, olivine at mantle depths transforms into a denser structure called wadsleyite, and at greater depths into ringwoodite, and at still greater depths into bridgmanite, each transformation releasing a small amount of energy and altering the seismic properties of the rock. On a lava world, the equivalent transitions occur in a material that is partially or fully molten, and their effects on the density of the melt, and thus on the direction of the convective flow, become important constraints on how heat moves within the planet. Material that is buoyant and rising near the surface may become denser than its surroundings at some depth and stall, or it may pass through a density crossover and continue rising in spite of it. The interior of such a planet, traced from surface to center, is a layered sequence of competing pressures and temperatures, each controlling the state of the material at that depth. The whole structure in continuous, slow negotiation with itself. None of this interior complexity is visible from outside. What is visible, what a telescope observing a lava world can measure, is what the planet emits, thermal emission from the dayside surface. The phase curve of that emission as the planet moves in its orbit. The faint chemical signatures absorbed or emitted by the thin mineral atmosphere. These are the only signals that escape the magma ocean and carry information about what lies below, and the interpretation of those signals depends on models of the interior physics, models that incorporate what is known about the viscosity of molten rock, the convective efficiency of a magma ocean, the electrical properties of silicate melt at extreme temperatures, and the solidification behavior of rock near the solidus. The observations constrain the models. The models make predictions about the interior. The interior cannot be directly seen. There is something clarifying about this situation. The deepest physics of a lava world, the convective overturn, the lateral circulation, the mush zone, the possible magnetic field, exists at a scale and a distance that no instrument can directly access. The science rests on what can be measured from thousands of light years away, and on what the laws of physics say must be true about fluid rock under extreme conditions. Between those two anchors, observation and theory, the picture of what these planets are like below their glowing surfaces is built carefully, one constraint at a time. It is not a complete picture. It may never be complete. But it is more than nothing, and it grows with every new observation. The magma ocean of a lava world is a body of fluid with deep time written through it. A planet that has maintained a tidally locked close orbit around its star for billions of years has had its magma ocean, if it formed early, if it persisted, flowing and convecting and circulating for spans of time that dwarf the age of anything familiar. The oldest rocks on Earth, the ancient cratons that have been geologically quiet for 3 billion years or more, have held their shape for an interval that feels geological and deep. The magma ocean of a lava world has been flowing since before those rocks were cold. Its convective cells have overturned more times than there are grains of sand in any desert. Its interior has been thoroughly mixed many thousands of times over into a chemical homogeneity that solid planets can never fully achieve. If there is anything buried in its deep interior, any remnant of the original composition of the planet's building blocks, any record of the chemistry of the protoplanetary disk from which it formed, it has likely been thoroughly stirred into the present. That stirring is itself a kind of loss and a kind of preservation. The planet's memory of its formation is gone, dissolved into the general composition of the melt. But the melt itself carries everything. Every element that was part of the original body of the planet is still there, somewhere in the ocean, redistributed by convection into a more or less even distribution throughout the fluid. Iron and silicone and oxygen and magnesium in proportions that reflect the composition of the original material. Trace amounts of rarer elements, carried upward by the convection and lost gradually to the thin atmosphere, and from there to space, or retained in the melt where they contribute their own small effects to the density, the viscosity, and the electromagnetic properties of the fluid. The ocean does not remember where everything came from, but it holds everything still in the heat. Across the day side, the slow upwellings continue, fractionally brighter at their centers, fractionally darker at their margins, where the descending material is coolest. They cover the hemisphere in a mosaic that shifts too slowly to observe directly and too continuously to ever be still. The host star hangs in the sky above, if sky is the word for the thin, incandescent mineral vapor that serves as an atmosphere, so close and so large that its disk occupies a significant arc of the planet's entire visible hemisphere. The light that falls on the surface is not the gentle, diffuse light of a distant star. It is something closer to the radiation inside a kiln, direct, intense, and arriving without the softening of distance. The surface absorbs it, emits it again as thermal radiation, channels it downward through the convective cells, and redistributes it across the interior in a circulation that is the planet's equivalent of a heartbeat. On the night side, where the star's light does not reach, the surface has given up most of its radiation to the cold of space. The temperature has fallen, slowly, to the point where the thin crust of crystallized silicate has formed above the still warm interior. The crust is dark. In the absence of starlight, and with the surface temperature below the point of significant thermal glow, the night side of a lava world would be very nearly black. The only light would be a faint deep red emission from the warmest regions, from the mush zone at the edge of the day side, from cracks in the thin crust where the hot interior is briefly exposed, from the slow dark churn of barely warm rock at the surface. Anything that could perceive that surface from above would see something very close to total darkness, broken only by the faintest hints of warmth at the margins. The terminator line between these two hemispheres is the sharpest geological boundary in the known inventory of planetary surfaces. It is not a coastline, which is irregular and constantly moving. It is not a mountain range, which is gradual and worn. It is the permanent edge of sunlight, a circle drawn around the planet by the geometry of its orbit and the fixity of its rotation, never moving, never eroding, maintaining its position with the same precision that the planet maintains its orbit. On one side, a vast ocean of glowing molten rock stretching to the substellar horizon. On the other, dark solid ground, or nearly solid, cooled to the point where the glow is gone and only heat remains, buried below a fragile lid of crystallized stone. Standing at the terminator, present at the terminator, in whatever form the physics allows, would be to stand at the most extreme geological boundary accessible in any planetary system we know. To one side, the temperature is high enough to vaporize steel. To the other, the surface has cooled below the point at which silicate melts, though the rock beneath is still warm, still close to the edge of its own softening. The boundary does not move with the passage of hours, because there are no hours here, no sunrise, no sunset, no daily cycle of any kind.